Tonight a comet 6.6 miles wide passes closer than it has in 59 years. Its name is Tempel 2, and we have known it was coming since 1873. We can tell you where it will sit in the year 2029. That certainty is the most dangerous thing about this whole story, because the comets that could actually end us arrive with no file at all. They come from any direction, at 3 times the speed, with months of warning. So here is what the next 3 hours are really about tonight. If we can see one comet coming from 153 years away, why are the ones we cannot see the ones that could finish us? Hit subscribe so you do not miss these briefings, and tell me in the comments where you are watching from. Let's get into it. Part 1. The rock we have watched for 153 years. Right now Tempel 2 sits 0.414 astronomical units from this planet. Converted into kilometres, that is roughly 62,005,000 of them. In terms your body can process, it is 161 lunar distances away. Shrink the Earth to a marble on your kitchen table tonight. The comet would sit about 1.5 kilometres down the road from you. That is the closest this object has come to us since the summer of 1967. 2 days ago, on August 2nd, it passed through perihelion at 1.418 astronomical units. Perihelion is simply the point in an orbit closest to the Sun. It is when a comet takes the most heat and works the hardest. Closest approach to Earth is an entirely separate event with separate causes. It depends on where our own planet happens to be parked in its orbit. Those 2 moments almost never line up for any comet in any given year. This year they line up to within about 48 hours of each other. That single coincidence is the whole reason anyone is talking about tonight. The comet is not doing anything unusual or unexpected in its own behaviour. Earth is simply standing in an unusually good place at an unusually good time. David Dickinson, writing for Universe Today in July, called this its most favourable appearance since 1967. The observing site's southern comets went further, calling it the best of the 21st century. I want to add one footnote, because precision matters more than enthusiasm here. The genuinely best modern apparition of this comet happened in 1925. It came within 0.35 astronomical units and reached magnitude 6.5. 1967 was 0.39, and tonight is 0.414. So when you hear best in 59 years, understand exactly what that phrase covers. It means best inside the era when good instruments were consistently pointed at it. That framing is accurate, and it is narrower than most headlines suggest. Now I need to manage your expectations, because much of this week's coverage has not. You are not going to walk outside tonight and see this comet with your eyes. At its brightest, Tempel 2 sits at roughly magnitude 8 in the sky. Some forecasts put it at 7.4, and Star Walk lists it at 8.7. A handful of outlets have said 10, which tells you how soft the estimate is. The faintest thing a person with good vision can see is around magnitude 6. That requires a genuinely dark sight, far from any town or highway. Magnitude 8 is roughly 6 times fainter than that already difficult limit. NASA's own guidance this week has been consistent and unglamorous about what is required. You need binoculars at minimum, and a small telescope is considerably better. It sits low in the southern sky at a declination of around minus 24 degrees. Southern Hemisphere observers have a real advantage on this one. Northern city observers are hunting a faint smudge near a light-polluted horizon. I am telling you this at minute 4 rather than minute 90 on purpose. I would rather you trust the numbers than feel cheated by the view. Because the interesting thing about this object was never how it looks. It is one of the largest comet nuclei that regularly crosses the inner solar system. It is also one of the darkest objects ever measured by anybody, anywhere, it is functionally almost entirely dead, and it is dragging a river of grit behind it that we have photographed. The comet is currently tracking through Aquarius and Capricornus toward Piscis Austrinus. It sits near opposition at a solar elongation of about 164 degrees. At closest approach, it crosses the background stars at roughly half a degree per day. That is the apparent width of a full moon every 24 hours. On June 30th, it passed about 45 arc-minutes south of the Saturn Nebula. That object is a planetary nebula catalogued as NGC 7009. The conjunction produced some of the better photographs of this entire apparition, and on July 20th and 21st, something happened that almost nobody reported. Earth crossed directly through the plane of this comet's orbit. That event produced the single strangest image of the year, and I will show you why. But to understand it, you first need to know what this object is made of, because Tempel 2 is not remotely what people picture when they hear the word comet. Part 2. The darkest thing in tonight's sky. Ask anyone to picture a comet, and they will picture something bright. A ball of ice, a white streak, a glow against a black sky. Tempel 2 is darker than charcoal. The measurement that establishes this is called geometric albedo. It is simply the fraction of sunlight that a surface throws back at you. Fresh snow has an albedo around 0.8, bouncing back 80% of incoming light. Asphalt sits around 0.1, which is why parking lots get hot. The moon is about 0.12 and looks bright only against a black sky. The nucleus of Tempel 2 has a measured albedo of 0.022. It reflects a little over 2% of the light that lands on it. Hold a piece of this comet under a desk lamp in your kitchen. It would look like a lump of coal that somebody had already finished burning. There are very few surfaces anywhere in the solar system darker than this one. To put that in a comparison, you can check yourself. Fresh asphalt reflects about 4%. This comet reflects roughly half what a new road surface does. That darkness is not because comets are built out of dark material. Water ice is bright, and the interior of this object is bright. What you are seeing from outside is a crust, and the crust has a history. Over hundreds of orbits, solar ultraviolet radiation has cooked the surface hydrocarbons. They have been baked into a layer of complex tarry organic compounds, sealing the object shut. Think of a pie left too long in a hot oven. The filling is still soft, but the top has hardened into a dark lid. Nothing gets out except through cracks in that lid. Those cracks are the strangest part of this whole object, and I will come back to them. Now the size, because the number in front of this briefing needs to be defensible. The accepted mean diameter of the nucleus is 10.6 kilometres. Converted, that is 6.6 miles across, which is where the figure comes from. That number is not a guess pulled from a press release somewhere. It sits at the end of a chain of careful measurements over decades. The cleanest link in that chain is a paper by Philippe Lamy and colleagues. Published in 2009, it used Hubble Space Telescope photometry to derive the radius. Their answer was 5.98 kilometres, plus or minus 0.04 kilometres. I want you to hold that uncertainty for a moment. Plus or minus 40 metres, for an object that spends most of its life beyond Mars. It is usually buried inside a cloud of its own escaping dust. That is an extraordinarily tight measurement for a target of that kind. A second study, led by Rosita Kokotonikova and published in 2017, refined the shape itself. Tempel 2 is not a sphere, and modelling it as one gets you the wrong answer. The spheroid fit gives a long axis of about 8 to 8.15 kilometres. The short axes come in around 4 to 4.3 kilometres each. That is an axis ratio near 1.9, which has a plain language meaning. This object is roughly twice as long as it is wide. Picture a potato. Now picture a very dark, very cold potato 8 kilometres long, tumbling end over end. That shape becomes important later when I explain why hitting one of these is difficult. Now, the comparison that everybody reaches for with a 10-kilometre object. The impactor that struck the Yucatan 66 million years ago is estimated at around 10 kilometres. So yes, the size figures genuinely overlap, and I am not going to pretend otherwise. But I want to be careful, because size is the least interesting variable in any impact. Treating it as the whole story is how people end up frightened of the wrong things entirely. Tempel 2 cannot hit Earth, in this century or the next one. Its minimum orbit intersection distance with Earth is 0.407 astronomical units. That figure describes how close the two orbital paths ever come to each other. Roughly 61 million kilometres separate the tracks, regardless of where either body sits. The orbits do not cross, and they do not come close to crossing. There is no scenario in any current dynamical model where this object reaches us. Now, the very next sentence has to matter more than that reassurance, because what makes an impact catastrophic is not the diameter of the thing, it is arrival speed, and composition, and the direction it came from. And on all three of those, this comet is the harmless version of a much worse object. One more number before I move on, and I find this one genuinely hard to hold. Tempel 2 is the second largest Jupiter family comet currently known to anyone. Only one, an object called Nujman 1, comes in larger than it. In raw dimensions, it is comparable to Halley's Comet itself. And Tempel 2 is, functionally, almost completely dead. Less than 1% of its surface is doing anything at all. Let me say that again, because it becomes the spine of everything later. An object the size of Halley, sitting in sunlight, and 99% inert. That is not normal behaviour for a comet in the inner solar system. The reason it is not normal tells you something uncomfortable about which comets are dangerous. But before I get there, I need to take you to a rooftop in Milan. Part 3. The mission we cancelled to save Cassini. On the 4th of July, 1873, Wilhelm Tempel was working at the Vera Observatory in Milan. He found a faint smudge that had not been in that patch of sky before. Tempel deserves a moment here, because his story is not the usual one. He was born in Saxony and trained as a lithographer, not as an astronomer. He had no university position when he started, and he bought his own telescope. Over a working lifetime, he discovered 21 comets and a number of nebulae. One of those nebulae would later be struck by a NASA spacecraft, which is a coincidence worth remembering. The comet he found that night is catalogued as 10P Tempel 2 today. The P simply stands for periodic, meaning the object comes back on a schedule. The 10 means it was the 10th comet whose periodicity was firmly established anywhere. That is a very low number in a catalogue with hundreds of entries. There are now well over 400 numbered periodic comets on the books. Since 1873, this comet has come back around 29 separate times. Astronomers successfully observed it at 24 of those returns. The 5 misses were geometry, rather than neglect on anybody's part. Sometimes the comet arrives on the far side of the Sun entirely. There is simply nothing to point a telescope at in those years. The observation arc currently stands at 130.8 years. That term describes the span between the first and most recent recorded position. The catalogue holds roughly 5,900 individual observations of this single object. I want you to sit with what that number actually represents in human terms. 5,900 times, a person pointed an instrument at a specific patch of sky. They found a faint moving smudge, measured its position against fixed stars, and wrote the number down. That happened across 130 years, through 2 world wars. It happened across the transition from photographic plates to electronic detectors. Every one of those measurements feeds the solution telling us where the comet sits tonight. That is why the orbital numbers are as sharp as they are. Aphelion, the far point, sits at 4.71 astronomical units, just outside Jupiter. Perihelion sits at 1.418, just outside the orbit of Mars. Eccentricity is 0.537, and inclination is 12.03 degrees. That low inclination means it runs near the plane of the planets rather than cutting across it. The orbital period is 5.36 years, and next aphelion falls on April 12, 2029. None of those figures are estimates or approximations by anyone. They are the output of 130 years of accumulated measurement. That is why I can tell you with real confidence that this object is harmless. Now here is the detail about Tempel 2 that almost nobody knows. It is the closest this comet ever came to being genuinely famous. In the late 1980s, NASA was building a mission called CRAF. The letters stand for Comet Rendezvous Asteroid Flyby, and the design was ambitious. It would be a Mariner Mark II spacecraft, structurally a twin of the Cassini probe. Same bus, same architecture, built at the same time to share development costs across programs. And the original prime target of CRAF was Tempel 2. The plan was not a flyby, and that distinction matters enormously. A flyby gives you a few hours of data, and then the object is gone. The plan was to fly out and match orbits with the comet directly. Then it would station keep alongside for 2.6 years. It would ride with the comet as it fell inward toward the sun, watching the crust heat up from a few kilometres away, watching the first jets break through that tarry lid in real time, watching the coma inflate around the spacecraft across an entire perihelion passage. We have never done that with any comet. We still have not done it. CRAF was cancelled in 1993, and the paperwork is public. The Government Accountability Office report is filed under NSIAD 94-23. Cost overruns on the shared Mariner Mark II program had reached a breaking point. NASA had to choose between the two spacecraft, and it chose one. The money that would have flown to Tempel 2 went to Cassini instead. I want to be fair about that trade, because it was not a foolish decision. Cassini became one of the most productive missions in the history of planetary science. Dropping the Huygens probe onto the surface of Titan happened because of that money. Finding the water plumes erupting at Enceladus happened because of that money. 13 years at Saturn happened because somebody made a hard call in 1993. But there is a consequence, and tonight is the night to state it plainly. The second largest Jupiter family comet we know of has never been visited. The one with the tightest measured nucleus in the entire catalogue. The one passing closest to us tonight in 59 years. No spacecraft has ever photographed its surface at any resolution. Everything I have told you about its shape and its darkness comes from light. Read by telescopes tens of millions of kilometres away over a century. Hold that, because it connects directly to the uncomfortable half of this briefing. We are extraordinarily good at measuring comets from an enormous distance. We are almost entirely inexperienced at actually reaching them. And to understand why reaching them is so hard, you need the machine itself. What a comet is, physically, when it starts to work. Part 4, 4,000 years of people writing it down. I want to come back to the ledger, because I have been leaning on it all night. The observation arc, the 5,900 measurements, the 2,000-year record on Swift-Tuttle. Where does a 2,000-year record actually come from? Nobody in '69, before the Common Era, was doing planetary defence. The answer is that they were doing something else entirely, and we inherited it. Chinese court astronomers kept systematic records of unusual sky events for millennia. Comets, eclipses, novae, sunspots. The motivation was political rather than scientific. A comet was read as a signal about the mandate of the ruling house. Recording it accurately mattered because interpreting it mattered. So they wrote down what they saw. Dates, positions relative to known star groups, brightness, the direction of the tail. Then they filed those records in dynastic histories that were copied and preserved. Those records are the reason Brian Marsden could nail down Swift-Tuttle. He was not reading them as astronomy. He was reading them as data. 2,000 years of positions, recorded by people with entirely different priorities. The same thing happened with Halley's Comet. Its returns have been traced back through Chinese, Babylonian and European records. Sightings going back to 240 before the Common Era have been matched to it. Every one of those was recorded by somebody who had no idea what they were building. This is the part of the field that I find genuinely moving, and I will be brief about it. The reason we can be relaxed about the dangerous objects is accumulated attention, not cleverness, not technology. Attention, sustained across generations by people who never coordinated. A court astronomer in the Han dynasty. A monk copying a chronicle. Wilhelm Tempel on a rooftop in Milan in 1873. An amateur in Japan finding a lost comet in 1992. None of them worked on the same problem. Together, they built the only defense that has ever actually worked. And that is why the long-period comet problem is structurally different. It is not a technology gap in the usual sense. It is a gap in the ledger. There is no entry for an object arriving for the first time. There cannot be. The record only helps with things that came before. Now, let me put a number on how thin our coverage actually is. The systematic era of comet observation is roughly 400 years old. That is from the invention of the telescope to tonight. Careful positional astronomy is closer to 300 years old. Photographic records go back about 150. And automated all-sky surveys have existed for roughly 30 years. 30 years of complete coverage. Against a hazard whose arrival interval is measured in millions of years. Here is a way to feel that ratio. Imagine trying to work out how often a river floods. You have detailed measurements from the last 30 seconds. And you are trying to predict a flood that happens once a century. That is not a criticism of anyone's methods. It is a statement about the sample size available to anybody working on this. Every estimate of long-period comet frequency rests on a very short baseline, which brings me back to something I mentioned earlier and want to close properly. The 1% figure from the decadal survey, the 25% hazard figure from Morrison and Chapman. Both of those numbers are derived from the record we have, and the record we have covers a sliver of the relevant timescale. Nobody working on those estimates would claim otherwise. The uncertainty is stated openly in the underlying papers, but it does mean something specific about how you should hold those figures. They are the best available inference from a genuinely thin dataset. They are not measurements of a well-characterized population, and that thinness runs in one direction. The objects most likely to be missing from a short record are the rare ones. Now I want to return to the sky above you tonight, because there is a point coming. Everything I have described about the ledger applies to the comet passing overhead. 153 years of entries, 5,900 lines in a catalogue. That is why I can tell you it is harmless and mean it. But there is a detail about that ledger I have not mentioned yet, and it is the reason this specific comet keeps producing surprises. Part 5. 4,000 years of reading them wrong. Before anyone could calculate an orbit, comets meant something, and what they meant was almost always bad. The pattern is remarkably consistent across cultures that never contacted each other. A comet appears without warning in a sky that is otherwise clockwork. Everything else up there repeats on a schedule. Stars return, planets wander predictably, the moon runs its cycle. Then something arrives that was not there, stays for weeks, and leaves. Every ancient system of sky reading treated that as a message. In China, the interpretation was political, and rulers took it seriously. A comet signalled a problem with the mandate of the ruling house. That is precisely why those records were kept so carefully. The observations that later let Brian Marsden pin down Swift-Tuttle exist because of that. In Europe, the association ran toward war, plague, and the death of kings. The most famous example is stitched into the Bayeux Tapestry. Halley's comet appeared in the spring of 1066. The tapestry shows it above a crowd of pointing figures, with Harold on his throne. That same year Harold lost at Hastings, and England changed hands permanently. The comet did not cause the Norman conquest, but it arrived in the same year, and that was enough for 11th century readers. In 1456, another return of Halley coincided with Ottoman advances into Europe. The comet was recorded across the continent, and the interpretation followed the usual pattern. Now I want to trace what actually broke that association. Because it did not break gradually. Edmund Halley did it, using Isaac Newton's mathematics, in 1705. He examined the recorded paths of comets seen in 3 separate years, 1531, 1607, and 1682. And he noticed the orbital elements were nearly identical across all 3. His conclusion was that these were not 3 comets at all. They were 1 comet, returning roughly every 76 years. Then, he did the thing that made it science rather than an observation. He predicted the next return. He said it would come back around 1758. Halley died in 1742, 16 years before the test could happen. The comet returned in December of 1758, as predicted. That single successful prediction ended something that had lasted 4,000 years. A comet was no longer a message about anyone's reign. It was an object on an orbit, subject to the same laws as everything else. The most feared thing in the sky had become a calculation, and I want to be precise about what changed in 1758. The comet did not become less dangerous that December. Nothing about its physical properties changed at all. What changed is that it acquired a schedule. That is the same distinction running through this entire briefing. Safety is not a property of the object. It is a property of the record we keep on it. But the old association did not vanish entirely, and I should be honest about that. It resurfaces whenever a bright comet arrives and the explanation lags behind. 1910 was one instance, with the cyanogen panic and the comet pills. There was another in 1997. Comet Hale-Bopp was discovered in July of 1995. Alan Hale in New Mexico and Thomas Bopp in Arizona found it independently. They found it on the same night, which is a coincidence worth noting. It became one of the most widely observed comets in recorded history. It stayed visible to the naked eye for about 18 months. During its approach, a rumour circulated that an object was following the comet. There was no object. The claim traced back to a misidentified star on an amateur photograph. Astronomers identified the star and explained the error publicly and quickly. The rumour spread anyway, and in March of 1997 it had consequences. 39 people in California died, having come to believe the claim. I mention that briefly because it belongs in the record. A bright comet, a false claim, and a vacuum that filled with something else. The lesson I take from these episodes is narrow and practical. In 1910 the measurement was correct, and the interpretation was catastrophic. In 1997 the measurement was wrong, and the correction did not travel. In both cases, the astronomy was available and public. It was simply not the thing that reached people. That pattern is worth holding as we move into the last stretch, because the long period comet problem has an information dimension, not only a technical one. Everything I have told you tonight is public. The decadal survey is downloadable this evening at no cost. The Choda's interview ran in a trade publication in 2023. Comet Interceptor's architecture was published in Nature Communications in 2019. The Rosetta Deuterium result is in Science. The Dark Comet paper is in Nature. None of it is hidden. All of it is uncovered. Which means the gap I have spent hours describing is not really a secret. It is something closer to an absence of attention, and attention is the entire mechanism by which any of this has ever worked. Halley did not build a better telescope than anyone else had. He read old records carefully and did the arithmetic. That was enough to change what a comet was. Part 6. 2 Tails and the River That Broke the Dirty Snowball. For about 70 years the working model came from an American astronomer named Fred Whipple. In 1950 he proposed that a comet nucleus is a dirty snowball, ice with dust mixed through it, sitting inert until sunlight arrives. Heat it and the ice turns directly to gas. The escaping gas drags the dust out with it, and that becomes the tail. That model was right in its bones and badly wrong in its proportions. The correction came from this specific comet, and I will get there shortly. For now, take the mechanism, because the mechanism is what matters here. A comet nucleus sitting out past Jupiter is completely inert. It is a few hundred degrees below zero, and nothing at all is happening. It is a rock made partly of ice, coasting on a long orbit. As it falls inward, the surface temperature begins to climb steadily. At a certain point, the water ice does something unfamiliar to everyday experience. It does not melt into liquid the way ice does in a glass. It sublimates, going directly from solid to gas with no liquid stage. There is no atmospheric pressure out there to hold a liquid phase together. The same thing happens to dry ice on a table, which smokes rather than puddling. That sublimating gas has to go somewhere, and it goes outward fast. It expands off the surface at a few hundred meters per second. As it goes, it grabs dust grains and carries them along with it. What you end up with is a cloud of gas and dust surrounding the nucleus. That cloud is called the coma, and for a large comet it swells enormously. It can grow larger than the planet Jupiter, while the solid object stays a few kilometers across. Then the sun goes to work on that coma, and it produces 2 tails. They point in different directions, and the reason is worth understanding. The ion tail is made of gas stripped of its electrons by ultraviolet light. Those charged particles get caught by the magnetic field inside the solar wind. They are swept almost exactly away from the sun, in a straight blue line. It does not trail behind the comet the way people assume. It points anti-sunward regardless of which direction the comet happens to be moving. When a comet heads away from the sun, its ion tail runs out in front of it. The dust tail works on entirely different physics, and looks different as a result. Dust grains are too heavy for the solar wind to grab and carry. What pushes them is the physical pressure of sunlight itself striking the grains. That force is far weaker than the magnetic one acting on the ions. So the dust drifts outward slowly while continuing to orbit alongside the nucleus. The result is a curved, broad, yellowish tail lagging along the comet's orbital path. 2 tails, 2 separate mechanisms, 2 different directions in the sky. When you see a photograph with one straight thin tail and one curved fan, you are looking at the difference. A magnetic field on one side and a beam of light on the other. And then there is a third structure that almost nobody discusses at all. Tempel 2 produces it better than nearly any comet in the sky. Stay with me, because this is where the object stopped being a curiosity. This is where it rewrote a textbook. In 1983, a satellite called IRAS was surveying the sky. The name stands for Infrared Astronomical Satellite, and it did the first all-sky infrared survey. Infrared light is heat rather than brightness, which changes what you can see. It sees things that are warm rather than things that are reflective. In practice, that means it sees dust extremely well. When IRAS looked at Tempel 2, it found something along the orbit, and that something was not a tail. A tail is made of small particles, micron scale, that get blown off the orbital path almost immediately. What IRAS found was a narrow band of large particles instead. They sat almost exactly on the comet's orbital track, stretching enormous distances in both directions, ahead of the nucleus and behind it. Not blown anywhere at all, just following. This structure is called a dust trail, and the definitive early work is specific. A paper by Mark Sykes, Diane Leon and Russell Walker, published in Icarus in 1990. The title was simply The Tempel 2 Dust Trail. The particles in it are large by any cometary standard, bigger than 1 millimetre across, and in the forward portion, grains of 6 millimetres or more. These are not specks of smoke drifting in sunlight. These are grains of grit roughly the size of a peppercorn. The reason they sit in the orbit rather than getting swept away is speed. They left the nucleus at only a few meters per second. Walking pace. They dribbled off rather than being blasted away. Once free with no meaningful force acting on them, they simply kept orbiting. They spread out slowly along the track over decades and centuries. Sykes and Walker went on to measure the trails of 8 separate comets. They calculated meteoroid production rates running from 4 to 250 kilograms per second. A separate analysis by Marco Full put Tempel 2 near 100 kilograms per second. That figure applies around perihelion, which is roughly where the comet sits tonight. 100 kilograms of grit, every second, shedding into a river of debris. That river stretches for tens of millions of kilometres behind and ahead. Now here is why that number broke Whipple's model completely. Total up the mass leaving a comet as gas, then total up the dust. The dirty snowball model predicts that gas should dominate the accounting. Ice is the engine, and dust is the passenger in that picture. But when the trail measurements came in, the ratio went the other way entirely. For Tempel 2, the dust-to-gas mass ratio is roughly 3 times more solid material coming off than gas. Sykes proposed a revised term for these objects in 1993. Not a dirty snowball at all. A frozen mud ball. An object that is mostly rock and dust held together by ice. In that picture, the ice is not the substance of the thing. The ice is the glue. Let me give you the analogy, because this distinction becomes lethal later on. A snowball is a thing you can hit successfully. It has structure and it transmits force through itself. Strike it hard and the entire object moves away from you. A mudball frozen for 1,000 years is a completely different target. Its surface has been baked into a tarry crust by ultraviolet light. It is porous, and it is weak, and its density sits well underwater. That means large parts of the interior are simply empty space. Hit it hard and you do not push it anywhere. You punch a hole in it, or you break it into pieces. And those pieces go in directions your model never predicted. Hold that, because I will bring it back when the stakes are real. Now this year the trail did something remarkable, and this is the July event. Earth crossed the plane of the comet's orbit on the 20th and 21st. Think about what a dust trail is geometrically for a moment. It is a thin sheet of debris lying flat in the plane of the orbit. Most of the time we view that sheet from above or below at an angle. Seen that way, it looks like a diffuse smear against the background sky. But when our planet passes exactly through the plane, the view changes completely. We are looking at the sheet edge along its length. All that debris, spread over tens of millions of kilometres of depth, stacks up. It compresses along our line of sight into a single razor-thin line. Between roughly July 18th and July 22nd, that line stretched enormously. It ran across more than 30 degrees of sky at its best. Sky and telescope covered it, and an astrophotographer named Dan Bartlett assembled a mosaic on July 16th. It is one of the cleanest images ever taken of this phenomenon anywhere. A comet, and behind it, running clean to the frame edge, its own history. Because that is what a dust trail genuinely is when you photograph it. It is not a current event or a live process at all. Sykes and his colleagues concluded the trail material records a mission over a few hundred years. You are photographing everything the object has lost, laid out in a straight line. Which raises a question I have been circling for 20 minutes now. If this comet sheds 100 kilograms a second, and has for centuries, something is wrong. Because 99% of its surface is doing absolutely nothing at all. Part 7. The colour that took 90 years to explain. Look at any photograph of tonight's comet, and you will notice something. The coma around the nucleus glows green. That green appears in almost every comet photograph taken in the last decade, and most coverage this week has attributed it to the wrong chemical entirely. The explanation you will read is cyanogen, and cyanogen is genuinely present. But it is not what makes the glow green. The green comes from diatomic carbon, 2 carbon atoms bound to each other written as C2. Chemists sometimes call it dicarbon. Cyanogen is also in the coma, and it does emit light. But it emits in the violet and the ultraviolet, not the green. Getting that right matters, because dicarbon carried a genuine mystery for 90 years. Here is the puzzle that stood unsolved for most of a century. The green glow appears in a shell around the nucleus of a comet. It never extends into the tail. Not in any comet, ever, in any photograph anyone has taken. The tail can be blue, or yellow, or white. The tail is never green. The German physicist Gerhard Herzberg proposed an explanation in the 1930s. He theorized that sunlight must be destroying the dicarbon molecules directly. They would be broken apart before they could travel far enough to reach the tail. That would explain the boundary neatly. But theorizing a mechanism and demonstrating one are entirely different things. Nobody could reproduce the process in a laboratory. The molecule is difficult to make and more difficult to study. For roughly 90 years the explanation sat there, plausible and unproven. In December of 2021, a team at the University of New South Wales finished it. Jasmine Borsovsky and Klaas Nauta led the experimental work in Sydney. Timothy Schmidt was the senior author on the resulting paper. They published in the Proceedings of the National Academy of Sciences. What they did was build dicarbon inside a vacuum chamber. Then they took it apart using ultraviolet lasers. That confirmed the photodissociation pathway Herzberg had suggested decades earlier. Schmidt summarized the result in plain terms afterward. He said they had proven the mechanism by which dicarbon is broken up by sunlight. He explained that this is why the green coma shrinks as a comet nears the sun, and why the tail of a comet is never green. So when you look at tonight's comet and see that glow, understand what it is. You are watching a chemical process being destroyed in real time. The green exists only in a narrow zone, the zone where molecules have been released but not yet dismantled by light. It is a boundary rather than a substance. 90 years from a hypothesis to a laboratory confirmation. For a colour. Now I want to bring the other chemical back into this, because cyanogen has a history, and the history is instructive. Cyanogen is a carbon and nitrogen compound. It is genuinely toxic in sufficient quantity. And in 1910, its presence in a comet caused a global panic. Halley's Comet was returning that year, and the calculations showed something specific. In May of 1910, Earth would pass through the outer part of its tail. Closest approach was about 0.15 astronomical units. That is roughly 22 million kilometres, around the 18th to 20th of May. On the 7th and 8th of February 1910, astronomers at Yerkes Observatory acted. They ran a spectroscopic analysis of the comet's tail. Spectroscopy splits light into its component wavelengths for examination. Every molecule leaves a specific signature in that spread. It is a chemical fingerprint written in light. What Yerkes found in Halley's tail was cyanogen. That measurement was correct. There was cyanogen in the tail. Then, the French astronomer Camille Flammarion made a public statement. Flammarion was widely read and widely quoted across Europe and America. He speculated that the gas might impregnate Earth's atmosphere, and that it could possibly snuff out all life on the planet. That statement went around the world in weeks. People sealed their doorways and their windows shut. A market appeared in comet pills, sold openly as an antidote. Gas masks sold in quantity. A broker in Los Angeles reportedly sold comet insurance to worried clients. The reality was almost comically different from the fear. A comet tail is a better vacuum than anything we can build in a laboratory. The cyanogen was present in trace amounts, and it was spread across a volume so vast the quantity reaching us was nothing. Earth passed through the tail of Halley's Comet in May of 1910. Not one person noticed anything at all. So why do I want you holding 1910 in your head tonight? 2 reasons, and the first one is about how information fails. This is the cleanest historical example of a correct measurement causing a panic. Yerkes was right. There was cyanogen. Everything after that was people filling a gap with fear. The second reason is the one that unsettles me, because the panic in 1910 was about a comet everyone could see. Halley was bright, tracked, predicted and named. People had months to work themselves into that state. The comets I've been describing all night do not offer that. They arrive without names until they are already inside Jupiter's orbit. There is no year of newspaper coverage building toward a date on the calendar, which raises a question I have not addressed yet. Where do those objects actually come from? Because the Oort cloud is something we have never seen. Not one telescope has ever imaged it, and we are almost certain it is there. Part 8. The comet that is 99% dead. I told you less than 1% of this surface is active. That is the central anomaly of this object, and it points somewhere larger. A young comet freshly arrived in the inner solar system behaves very differently. It is active across most of its surface, because ice sits close to the surface everywhere. Heat it, and the entire object outgasses at once. Tempel 2 does not do that at all. The Kochertnikova study describes it as one of the most highly evolved comets known. Highly evolved is a polite way of saying old and worn out. It has made this trip so many times that the accessible surface ice is gone. What remains is sealed under the tarry crust I described earlier. What is left is a handful of small vents in that lid. And the behaviour of those vents produces 3 separate oddities in the data. The first oddity is timing. Tempel 2 barely outgasses until about 2 to 3 months before perihelion. Most comets show a gradual ramp upward as they approach the Sun. This one stays quiet, and then it switches on. That is consistent with a crust that must reach a threshold temperature. Nothing underneath can break through until the lid itself gives way. The second oddity is asymmetry, and it was spotted a long time ago. The astronomer Zdeněk Šekinina noted it back in 1979. This comet is significantly brighter after perihelion than before it. That holds true even at the identical distance from the Sun. That should be impossible if activity depended only on how much heat arrives. Later work by Matthew Knight and colleagues tied it to geometry. The spin axis orientation matters, along with the location of a single active region. That region sits near one of the poles of the nucleus. The comet has to rotate it into sunlight before much of anything happens, and the geometry only works out properly on the outbound leg of the orbit. The third oddity is the strangest of them, and it makes this object scientifically important, far more important than its public profile would ever suggest. The rotation of Tempel 2 is slowing down. The measured synodic rotation period is 8.948 hours. The uncertainty on that is 1/1000th of an hour, but it has not always been that number, and that is the point. Knight and colleagues published work in 2011 and 2012 pulling apparitions together. In 1988 the period measured 8.932 hours. In 1999 it measured 8.941 hours. In 2010 it measured 8.950 hours. That is a lengthening of roughly 16 seconds per orbit. 16 seconds does not sound like very much of anything. It is the most important number in this entire briefing, because it means we caught a comet changing its own spin rate. In real time, across observations made decades apart, and we know the cause. The gas leaving that small polar vent is acting as a rocket engine. It is thrust, applied off-center, over months, on every single orbit, and it is torquing an object 8 kilometres long. Think of a garden sprinkler head spinning from the water pushing out of it. Same principle, running for centuries, on a mountain made of frozen mud. Tempel 2 was one of the first comets ever shown to be doing this, and I need you to hold that 16 seconds, because it comes back. When it does, it changes the shape of everything. There is one more anomaly in the file worth mentioning here. In 2010, the Spitzer Space Telescope imaged Tempel 2 at 4.5 microns. It found a fan of arcs on the sunward side of the nucleus. The opening angle of that fan was about 62 degrees. Arcs like that come from a strong, well-defined active region, or they come from a sequence of discrete outbursts over time. Either way, something structured is happening on that surface. And the disagreements do not stop with the arcs. Published diameter estimates have ranged from around 12 kilometres down to 10.6. Older work modelled it at 16.3 by 8.6 kilometres. The brightness forecasts for this apparition spanned 3 full magnitudes before it arrived. I want to be clear about what that spread means, and what it does not. It does not mean the underlying science is unreliable or sloppy. It means comets are genuinely, physically unpredictable objects at close range. Even the ones watched for 130 years keep surprising the watchers. Now take everything I have just described and put it together. An object whose spin changes because of its own escaping gas. An object whose brightness cannot be predicted within 3 magnitudes. An object that is mostly hollow, mostly crusted, and structurally weak throughout. Now imagine one of these inbound toward us, discovered 8 months ago. That situation is the second half of this briefing. But before I get there, I need to show you the leash. Because the leash is the entire reason we can see this one coming. Part 9. The leash Jupiter put on it. Every comet belongs to one of 2 broad families, and the difference decides everything. It is the difference between an object we can schedule and one that surprises us. Tempel 2 is a Jupiter family comet, and that classification is not loose language. It is defined by a quantity called the Tisserand parameter. It was worked out by the French astronomer Félix Tisserand in the 1890s. Let me explain what it actually measures, because it sounds abstract and is not. Take three bodies interacting gravitationally: the Sun, Jupiter, and a comet. The comet's orbit is not stable under those conditions. Every time it passes Jupiter, the planet yanks on it and reshapes the orbit. Energy gets traded, the comet speeds up or slows down, the path shifts. What Tisserand found is that one thing in that mess stays nearly constant. It is a specific combination of the comet's own orbital elements. It survives no matter how many times Jupiter kicks the object around. The individual numbers change wildly from encounter to encounter. That one combination does not, which means you can use it as a fingerprint on any new object. Calculate the Tisserand parameter for a comet you have never seen before. It immediately tells you whether Jupiter has been controlling that orbit. For Tempel 2, the value comes out at 2.965. Anything between 2 and 3 marks a Jupiter family comet. So the number is not merely telling us this object orbits near Jupiter. It is telling us Jupiter has been grabbing this thing repeatedly for a very long time. And it has parked the far point of the orbit at 4.71 astronomical units. That distance is essentially Jupiter's own distance from the Sun. That is the leash. Jupiter caught this comet, and it keeps catching it. Once every 5.36 years, the arrangement gets renewed. I want you to feel what that means in practical terms tonight. Jupiter is not a bystander sitting out in the cold outer solar system. It is a gravitational governor for the entire system. It takes objects that would otherwise run wild, long, unpredictable paths. It drags them into short, flat, regular orbits near the plane of the planets. It makes them boring. And boring is the same thing as safe. Because boring means we see them coming from a very long way off. Here is the version of this that I keep in my head. Picture a crowded room with 100 people walking in random directions. Now put one very large person standing in the middle of that room. Every time somebody passes close, he grabs their arm and swings them around himself. After a while, some fraction of that room walks neat circles around him, and you can tell me exactly where any of those people will be in 10 minutes. Jupiter does exactly that to comets. The ones it has grabbed are the Jupiter family. Tempel 2 is one of them, walking its circle since long before anyone watched. Now hold the rest of that image. Everyone else in the room is still walking randomly. Nobody has grabbed them, and nobody knows where they are going. That is the entire second half of this briefing waiting for us. But there is another comet in the sky this week, and it is different. That one actually reaches us. Part 10. The shell we have never seen. Everything I have told you about long-period comets rests on one assumption, that there is a reservoir of icy bodies surrounding this solar system. We call it the Oort cloud. Nobody has ever seen it. No telescope has imaged a single object in it. Not one member of that population has been directly observed in place. We are still confident it exists, and the reasoning is worth walking through, because it tells you how this entire field works. The argument was assembled by a Dutch astronomer named Jan Oort in 1950. He was studying the orbits of long-period comets that had already been observed, and he noticed 3 things in the data that did not fit anything else. The first thing was the aphelion distances. When you calculate where these comets reach their farthest point, a pattern emerges. A striking number of them peak at around 50,000 astronomical units. That is not a random spread, it is a pile-up at a specific distance. The second thing was the direction of arrival. Long-period comets come at us from every direction equally. There is no preference for the plane where the planets orbit. That is completely unlike asteroids, which cluster tightly in that plane. A random distribution of directions implies a spherical source. The third thing was the most telling of all. Very few of these comets showed orbits indicating they had visited before. Most were arriving on their first pass through the inner solar system. Their ices were pristine and had never been heated. Put those three observations together, and one structure explains all of them. A spherical shell of icy bodies, enormously far out, loosely bound to the Sun. Oort published that inference in 1950. 76 years later, we have still never seen it. The distances involved are genuinely difficult to hold in a human head. The inner edge is estimated somewhere around 2,000 astronomical units out. The outer edge may reach 100,000 astronomical units or more. Neptune, the outermost planet, orbits at 30 astronomical units. So the Oort cloud begins roughly 70 times farther out than Neptune, and it may extend 3,000 times farther than Neptune. Here is the analogy I find useful for that scale. Imagine the orbit of Neptune shrunk down to the size of a dinner plate. On that scale, the Oort cloud's outer edge sits about a kilometre away, and the entire volume between is essentially empty, which is why nothing out there has ever been detected. The objects are small, dark, and unimaginably far from any light source. Sunlight at that distance is 100 million times weaker than here. They are cold, black, and invisible until something knocks one loose. So what knocks one loose? Two mechanisms are understood, and both are gentle, which is exactly why they are dangerous. The first is the galactic tide. Our solar system orbits the centre of the Milky Way. It takes roughly 230 million years to complete one circuit, and the gravitational field of the galaxy is not uniform across that distance. The Sun feels one pull, and an object 50,000 astronomical units out feels a slightly different one. That difference is small, but it acts constantly over billions of years. It slowly stretches and reshapes orbits at the outer edge of the cloud. The second mechanism is stellar passage. Other stars in our neighbourhood are moving. Occasionally one passes close enough to disturb the outer Oort cloud directly. That has happened, and we have identified a case. A red dwarf called Schultz's star is estimated to have passed through the outer Oort cloud, roughly 70,000 years ago, well within the span of human existence. Astronomers have calculated that passage from the star's current motion and position. Neither mechanism throws a comet at us with force. That is the part people misunderstand about this process. A comet does not get launched inward at speed. What happens is far more subtle and far harder to predict. An object out there is barely bound to the Sun at all. Its orbital velocity is measured in tens of meters per second. Walking pace, over a distance of 1 trillion kilometers. Change that velocity by a fraction, and the orbit tilts. Instead of a vast circle, the path becomes a very long ellipse. One end still sits 50,000 astronomical units out. The other end now drops into the inner solar system. Think of a marble balanced on the rim of an enormous bowl. It takes almost nothing to tip it inward, and once tipped, it takes a very long time to arrive. But it is coming, and its arrival was decided 1 million years ago. That is the timescale of the mechanism that produces these objects. The nudge happens over hundreds of thousands of years. The fall inward takes hundreds of thousands more, and the final approach from Jupiter's orbit to ours takes months. So the process is slow beyond comprehension for nearly all of its duration. And then it is fast at exactly the moment when speed matters. There is one more property of these objects worth stating before we move on. A first-time arrival from the Oort cloud has never been heated by our Sun. That sounds like a minor detail, and it is not. It means the material on the surface is unaltered since the solar system formed. Roughly 4.5 billion years of storage at a few degrees above absolute zero. Everything else we can reach has been cooked. Every asteroid, every planet, every short-period comet, including tonight's. They have all been through the inner solar system repeatedly and lost their volatiles. A pristine long-period comet is the only sample of original material available, which is exactly why Comet Interceptor is designed to chase one. The scientific value of reaching one is enormous and nobody disputes it, so the same objects carrying the largest hazard also carry the most information. That tension runs through this entire field. The thing we cannot see coming is also the thing we most want to examine. Now here is the part that I keep returning to. Every long-period comet we have ever observed was already falling. The nudge happened before recorded history. The object has been on its way since before our species existed, which means the comet that would matter most is already in transit. It has been in transit for a very long time. It is out there right now, dark and cold and unnamed. And we cannot see it, because nothing out there reflects enough light to detect. So the only question that matters is when it becomes visible. And that turns out to depend on something nobody controls. It depends on which direction it happens to be coming from. Part 11. The other comet. The one that actually reaches us. Tonight, while Tempel 2 makes its closest pass in 59 years, something else is happening. A second comet is delivering material into Earth's atmosphere right now. You will never see that comet. It is nowhere near us tonight. It has not been near us since 1992. It will not come back until the 22nd century. You will see the debris instead. We call it the Perseid meteor shower, and it peaks on August 12th. The parent object is Comet Swift-Tuttle, and I need two numbers side by side. Tempel 2, the object passing tonight, measures 6.6 miles across. Swift-Tuttle measures 26 kilometres across, which is 16 miles. NASA's own description of Swift-Tuttle is worth quoting carefully here. The agency states it is more than twice the size of the object hypothesized to have caused the demise of the dinosaurs. Not comparable to that object. More than twice. Every August, Earth drives straight through the debris stream Swift-Tuttle has laid down. Grains of that comet enter our atmosphere at about 59 kilometers per second. That converts to roughly 132,000 miles an hour. They burn up 60 to 100 kilometers over your head. That is a Perseid. Every one you have ever watched was a piece of a 16-mile comet. Now, two practical notes. Because the 2026 shower has an unusual profile. The good news is the moon, which is usually the limiting factor. New moon falls on August 12th at 1737 Universal Time. That puts illumination at effectively zero on the peak night itself. That is as dark a sky as this shower ever gets. The complication is the rate, and it cuts the other way. The American Meteor Society still lists the nominal zenithal hourly rate near 100. But the International Meteor Organization expects lower numbers this year specifically. Their range runs somewhere around 30 to 50 meteors per hour. Earth is passing through a thinner section of the debris stream this time, so you get the best possible sky over a weaker than usual stream. Before I get to the third thing, one detail about the Perseids is worth having. The name comes from the radiant, which is the point the meteors appear to leave. That point sits in the constellation Perseus, which is where the shower gets its name. But the meteors do not come from Perseus in any physical sense. That constellation is hundreds of light years away and has nothing to do with it. What you are seeing is a perspective effect, and there is a good analogy for it. Drive into falling snow at night with your headlights on. The flakes appear to stream outward from a single point ahead of you. They are not coming from that point. You are moving toward them, and your motion creates the pattern. Earth does exactly that as it drives through Swift-Tuttle's debris stream. The radiant is simply the direction we are heading at the time. The other useful fact is about size. A typical Perseid meteor is produced by a particle around the size of a grain of sand. Some are smaller than that. They are visible from 60 kilometres up because of speed alone. 59 kilometres per second is enough to make a sand grain glow like a star, which tells you something about the energy in a fast-moving object. A grain of sand, arriving fast enough, produces a light visible across a county. Now scale that up to a nucleus 26 kilometres across. That is the arithmetic underneath Yeomans' estimate, which I will come to shortly. And there is a third thing happening on that same date. On August 12th, 2026, there is a total solar eclipse. Scientific visualization studio, the path of totality is specific. It runs across Greenland, Iceland, northern Russia, the Atlantic, Spain, and a corner of Portugal. Totality reaches up to about 2 minutes and 18 seconds at its longest, over Iceland. It is the first total solar eclipse over mainland Europe since August 11th, 1999. The European Space Agency notes the next one crossing most of the continent arrives in 2075. In Spain, totality falls around 8:30 in the evening local time. The sun will sit only 10 to 12 degrees above the horizon then. That will make it one of the stranger eclipses on record visually. So inside a 9-day window, look at what this sky is doing. A 6-mile comet at its closest approach in 59 years. The debris of a 16-mile comet burning overhead under a new moon. And the sun going out over Europe on the same night. None of those three events cause each other in any way. They are three independent clocks that happen to strike together. But I want to come back to Swift-Tuttle before I move on. There is a piece of its history most people have never heard. It is the closest the modern era came to a genuine planetary emergency. Stay with me for this one, because the dates matter enormously. Part 12. The date Brian Marsden could not rule out. In 1973, an astronomer at the Harvard-Smithsonian Center did something bold. His name was Brian Marsden, and Swift-Tuttle had gone missing. It had been observed in 1862 and then lost entirely. Nobody had seen it in over a century at that point. Marsden went back into the historical record and linked the 1862 observations to earlier sightings. Then, he published a prediction that the comet would return in 1992. He was betting a professional reputation on an object nobody had seen in 130 years. On September 26, 1992, a Japanese amateur astronomer found it. His name was Tsuruhiko Kiuchi, and he was looking exactly where Marsden said. Marsden's prediction was off by 17 days. That should have been the end of the story, and a triumphant ending at that. But once the comet was recovered, Marsden had real positional data to use. He ran the orbit forward through the coming centuries. And what came back was uncomfortable. Swift-Tuttle returns to perihelion in the year 2126. If that return slipped by about 15 days from the nominal prediction, the geometry changed. The comet would arrive at Earth's orbital position at the same moment Earth did. The date he calculated was August 14th, 2126. I want to be precise about why 15 days was not a comfortable margin. Marsden had just been wrong by 17 days on a prediction he expected to nail. 17 is a bigger number than 15. That is the entire problem in one line. And this is where the orbital geometry becomes genuinely alarming. Remember the minimum orbit intersection distance for Tempel 2. 0.407 astronomical units. The orbits never come near each other. For Swift-Tuttle, that figure is 0.0009 astronomical units. That is about 1,000 kilometres, roughly a third of the distance to the Moon. The orbit of Swift-Tuttle very nearly intersects the orbit of the Earth. It runs retrograde, inclined at 113 degrees to our plane. In plane terms, it comes at us against the traffic. Its velocity relative to Earth would run somewhere around 58 to 60 kilometres per second. So for a period in the early 1990s, something unusual was true. The largest object known to cross Earth's orbit had an impact scenario attached, and that scenario had a specific date on a specific calendar. What resolved it was history rather than better telescopes. Marsden worked with the comet historian Gary Cronk on the observational record. Together they matched Swift-Tuttle to Chinese records from 69 before the Common Era. They matched it again to observations from the year 188. Those two data points extended the observation arc enormously. It went from 130 years to over 2,000 years of coverage. With an arc that long, the orbital solution tightened dramatically. The 2126 impact was ruled out. Donald Yeomans ran the Near-Earth Object Program Office at the Jet Propulsion Laboratory. He has described what the refined solution actually says about that return. Swift-Tuttle passes on August 5th, 2126, at about 14 million miles. That is 23 million kilometres, roughly 60 times the Earth-Moon distance. There is a genuinely close pass in the year 3044. That one comes in around 1.6 million kilometres, which is still 4 lunar distances. So let me be completely clear, because this story gets distorted constantly. Swift-Tuttle is not going to hit Earth in 2126. That was a preliminary calculation from an incomplete orbital arc. Better data corrected it, exactly as the process is supposed to work. Anyone telling you otherwise is quoting a 30-year-old headline. But the reassurance lasts about one sentence, because Yeoman said something else. He went on record about the counterfactual, and the number he used is sobering. If Swift-Tuttle did strike Earth, he estimated the impact energy. He put it at about 300 times the collision that killed the dinosaurs. His conclusion was that it would be a very bad day for Earth. 300 times Chicxulub. Hold that number and notice something about it before we move on. Swift-Tuttle is the most dangerous large object we know of. That holds in terms of raw potential energy and orbital geometry together. And we have it completely mapped for the next 1,000 years. We know where it will be in 100 years. We have matched it to Chinese astronomical records predating the Roman emperors. The reason we can relax about the most destructive object in our neighbourhood is simple. We have 2,000 years of homework on it. Which brings me to the actual subject of tonight, because an entire category of object will never give us 2,000 years. Or 200 years. Or 2. Part 13. The ones that arrive without a file. I have spent an hour showing you objects on leashes. Tempel 2, held by Jupiter, tracked continuously since 1873. Swift-Tuttle, dangerous on paper, mapped back to 69 before the Common Era. Now I want to take the leash off entirely. Everything so far has been a short period comet, Jupiter family, or Halley type. They live inside the planetary region and their orbits are known. They come back on schedules we can publish decades ahead. Long-period comets do not work that way at all. A long-period comet comes from the Oort cloud. That is a spherical shell of icy bodies surrounding the entire solar system. It sits at distances so large that the numbers stop meaning anything useful. Objects out there are only loosely bound to the sun at all. A passing star, or a gravitational nudge from the galactic tide, is enough. One of them falls inward toward us, and when it falls from any direction whatsoever. The Oort cloud is a sphere, not a disk. Asteroids come at us from the plane of the solar system. That is where all the planets sit, and where all our survey telescopes look. A long-period comet can arrive from directly above the North Pole, or from underneath. or head-on straight into our orbital motion. It arrives faster too, and this is where the physics turns hostile. A typical near-Earth asteroid impacts at somewhere between 17 and 20 kilometres per second. Paul Weissman at the Jet Propulsion Laboratory calculated the long-period figure. He put the most probable impact velocity at 53.5 kilometres per second. Derek Richardson, an astronomy professor at the University of Maryland, works on planetary defense. He worked on the DART mission, and he puts the figure near 65. His assessment of what that means was blunt. He said they are bad news. Now, kinetic energy scales with the square of velocity. That is not a technical footnote. That is the entire story of this briefing. Triple the speed, and you do not get triple the energy. You get 9 times the energy. A recent analysis on the archive preprint server states it directly. Comet impact energies can be 9 times as large as asteroids of equivalent mass. So take a comet and an asteroid of exactly the same size and mass. Physically the same amount of material arriving at the same planet. The comet hits with 9 times the destructive energy, purely because of how fast it was moving when it got here. And now the number that matters more than any other tonight. How much warning would we actually get? Donald Yeomans wrote about this in his book on near-Earth objects. Princeton published it in 2013, and the wording is exact. He wrote that long-period comets are the most difficult objects to mitigate, and that the impact warning time would be measured in a few months, not years. A few months, not years. The working figure is around 9 months for a large inbound object, that is the interval between detection near Jupiter's orbit and arrival here. Paul Weissman's assessment came out similar to that. Current technology detects these objects at about 5 astronomical units out. That gives somewhat less than a 1-year warning in practice. Let me say that again, because I do not think it lands the first time. For an object arriving at 3 times the speed of an asteroid, carrying 9 times the energy per unit of mass it contains, coming from a direction our telescopes are not systematically watching at all. Our warning time is somewhere between 6 months and a year. Paul Chodas is the director of the Center for Near-Earth Object Studies. That office sits at the Jet Propulsion Laboratory in Pasadena. Knowing this is literally his job description. Speaking to Aerospace America in February of 2023, he was direct. He said 2 years warning is really short unless you have prepared a lot on the ground. He also said even a relatively small long-period comet would mean global devastation. And then he said the part I have not stopped thinking about since. He said neither the NEO Surveyor telescope nor the Vera Rubin Observatory changes this. Neither will detect long-period comets with much more warning than is possible today. That capability, in his words, is another generation of technology away. We are not about to fix this problem. The instruments currently being built do not fix it. Now I know the natural objection to everything I have just said. Surely the probability is so low that none of this matters. So let me put 2 numbers in front of you, and then I will explain why they do not contradict each other. Part 14. The direction nobody can look. I want to explain how we actually find these objects, because the method has a flaw built into its physics. Finding a moving object in the sky is conceptually simple. You photograph a patch of sky tonight. You photograph the same patch tomorrow night. Then software compares the 2 images and flags anything that moved. Stars stay put. Everything in the solar system does not. That is the entire principle behind every survey telescope operating today. The Catalina Sky Survey in Arizona, Pan-STARRS in Hawaii, the Zwicky Transient Facility in California, and now the Vera Rubin Observatory in Chile, which images the visible southern sky every few nights. This system works extremely well, and I do not want to undersell it. Before these machines existed, comet discovery was a human activity. Somebody had to sit at an eyepiece in the dark. They needed a good memory for what a specific patch of sky should look like. That is how Wilhelm Tempel found 21 comets in the 1800s. That is how George Alcock found his through a window in 1983. Now we find hundreds of objects a year rather than a handful. And that raises a question I get every time I cover this. Are we seeing more comets than we used to? Is something out there disturbing the outer solar system? The honest answer is that the sky has not changed. Our detection capability has. Go from a few hundred people watching small patches to machines watching everything. Your discovery rate rises by orders of magnitude immediately. The population did not change at all. The efficiency did. There is a good parallel for this in public health statistics. If a country doubles its testing capacity and diagnosed cases triple, be careful. You have not necessarily learned anything about the disease itself. You have learned something about the testing program. So there is no evidence that comet arrivals have increased. What increased is the fraction we managed to catch. But I want to point out something uncomfortable that follows from that. If our detection efficiency was historically very low, our baseline is built on an undercount. Every historical estimate of arrival frequency came from the record we managed to compile, with the instruments we happened to have at the time. I am not saying the numbers are wrong. They are the best estimates available, made by careful people. I am saying the error bars run wider than the headline suggests, and the historical bias runs in one direction only. You do not overcount the things you cannot see. Now here is the flaw I mentioned at the start of this part. Every method I just described requires the object to be in a dark sky. You are photographing a patch of night and looking for something faint. That works for any direction except one. You cannot look at the part of the sky where the sun is. An object approaching Earth from the sunward direction is invisible from the ground. Not difficult to see. Invisible, it sits in daylight, and it stays in daylight until it arrives. Every ground-based telescope on this planet is blind in that direction. That is not a funding problem or an engineering oversight. It is a geometric fact about observing from the surface of a planet. And objects do come from that direction. The sky is a sphere and there is nothing special about the sunward part. Roughly speaking, some fraction of all incoming objects approach through the glare. We have a demonstration of this, and it happened within living memory. I will get to it shortly, because it deserves its own section. There are partial solutions being pursued. Space-based infrared telescopes can observe closer to the sun than ground telescopes can. NEO Surveyor is designed to do exactly that for asteroids. Observing in infrared also helps, because dark objects that reflect poorly still radiate heat, but partial is the operative word in that sentence. NEO Surveyor was built to a congressional mandate about asteroids. Objects 140 meters and larger in near-Earth orbits. That is a specific population, and it is not the one worrying me tonight. Paul Chodas at the Center for Near-Earth Object Studies has been explicit about this. Neither NEO Surveyor nor the Rubin Observatory will detect long-period comets meaningfully earlier. That capability, in his words, is another generation of technology away. So let me lay out the full detection picture as it stands tonight. For asteroids in the plane of the solar system, we are good. Decades of warning on the large ones. A catalogue that grows every night. A proven method for finding them and refining their orbits. For long-period comets arriving from arbitrary directions, we are limited. Detection somewhere around 5 astronomical units when the object begins outgassing. That gives roughly 6 months to a year of warning. And for anything approaching from the sunward direction, we have effectively nothing. It arrives without any warning at all. Now hold those three cases together, because in February of 2013, all three were demonstrated on the same morning over the same country. Part 15. The objects that are lying about what they are. There is a category problem sitting underneath this entire briefing. I have been sorting objects into two boxes all night: comets and asteroids, icy things and rocky things, things that outgoes and things that do not. That division is less clean than it sounds, and over the last few years it has started coming apart. Start with the obvious case. An old comet like Tempel 2 has lost most of its accessible ice. Less than 1% of its surface does anything at all. Keep running that process forward across another few thousand orbits. Eventually the vents seal completely. The outgassing stops. What remains is a dark, rocky, inert object in a comet's orbit. At that point, what is it? Observationally, it is an asteroid. It has no coma and no tail. It reflects almost no light, and it moves through the sky like a rock. Physically, it is a dead comet with a mantle of ice buried under a crust. Astronomers have a name for these: extinct or dormant comets. And a meaningful fraction of the near-Earth asteroid population is thought to be exactly that: objects that used to be active and stopped. Now here is the part that has become interesting recently. In 2023, a group of researchers published work in Nature. Darrell Seligman was among the lead authors on the study. They examined near-Earth objects that showed no coma at all, no visible outgassing, no tail, nothing that would mark them as comets by sight. And they found that several of these objects were accelerating. Not gravitationally. Their measured positions did not match the predictions from gravity alone. The term the paper used was dark comets. An acceleration that gravity cannot explain has one straightforward cause. Something is leaving the object and pushing it, which means those objects are outgassing, quietly, invisibly, without producing enough dust to see. That is the same physics slowing tonight's comet by 16 seconds an orbit. It is just happening below the threshold where anything shows up in an image. I want to give you one more example of a category giving way. For a long time, the asteroid belt and the comet population were considered separate. Different origins, different compositions, different regions of the solar system. Then observers found objects in stable asteroid belt orbits that grow tails. They are called main belt comets, and they were identified in the early 2000s. They sit exactly where asteroids sit, and they behave partly like comets. Their existence suggests water ice survives in places nobody expected it to, which matters for where Earth's water came from, and for what an impactor might contain. Now think about what that means for the categories. We have objects classified as asteroids that are behaving like comets. They carry unpredictable non-gravitational forces on their trajectories, and nothing in their appearance tells you which ones they are. The practical consequence is about prediction rather than classification. When you compute where an object will be in 20 years, you use gravity. If the object is quietly thrusting, that computation drifts, slowly and in a direction you did not model. For most objects, the effect is tiny and irrelevant. For an object you are trying to intercept, it is not. I raise this because it undercuts a reassurance I offered earlier. I told you that asteroids are the predictable ones. Solid, inert, no rocket effect, orbits computable decades ahead. That is broadly true, and it remains the working assumption. But a fraction of that population is quietly doing something else, and we only found out because somebody checked the residuals carefully. There is a wider version of this problem worth naming. Every category in this field was built from what we could observe. Comets were things with tails, because a tail is what a telescope shows you. Asteroids were things without tails. The classification followed the instrument. Then better instruments arrived, and the boundary blurred. We found main belt comets, objects in asteroid orbits that outguss. We found dormant comets in near-Earth space. Now we have dark comets, which look like one thing and behave like another. And in 2017 we found an object from another star, which did not fit either box, and showed an acceleration nobody could explain. I want to be honest about what I am claiming here. I am not saying the science is unreliable or the categories are useless. They are useful, and they are being refined exactly as they should be. What I am saying is narrower. Confidence in this field tracks observation time, not category labels. We trust Tempel 2 because of 153 years of measurements. Not because it has been sorted into a box marked Jupiter family. An object we have watched for 1 week sits in a box 2. That box tells you almost nothing about what it will do. Part 16. 1% and 25% cannot both be right. In 2023, the National Academies published a document that sets priorities. It is the Planetary Science and Astrobiology Decadal Survey, covering 2023 to 2032. It shapes American work in this field for a full decade. Chapter 18, page 488, addresses comets directly. It states that long-period comets and interstellar objects allow little warning time. It states the statistical probability of Earth impact by a comet is much lower, around 1%, compared to the probability from near-Earth objects. Therefore, it concludes, near-Earth object impact prevention is the priority for the decade. Lindley Johnson holds the title of Planetary Defense Officer at NASA. He has put the same figure more plainly than the document does. He said the probability of an impact by comet is less than 1% of an asteroid impact. 1%. That sounds like a closed case and a solved problem. Now here is the second number, and it comes from equally serious people. The Encyclopaedia Britannica entry on Earth impact hazard draws on published work, specifically the analysis of David Morrison and Clark Chapman. It puts the hazard from long-period comets differently, perhaps as high as 25% of the hazard from near-Earth objects. The Planetary Society uses a similar split in its own materials. Asteroids around 75%, comets around 25%, 1% and 25% for what sounds like the same question. They are not the same question, and the difference is the whole point. The 1% figure is about frequency. How often does a comet hit us, compared to an asteroid? The answer there is, very rarely indeed. Asteroids are the overwhelming majority of impacts by simple count. The 25% figure is about hazard rather than frequency. It weights each impact by how much damage that impact does. Once you wait for damage, comets climb steeply in the ranking. Everything I walked you through explains why they climb. They move 3 times faster than asteroids do. They carry 9 times the energy per unit of mass. They tend to be large, because the small ones do not survive the trip, and you get months of warning instead of decades of it. So both numbers are correct, and they measure different things entirely. Comets are rare, and comets are disproportionately lethal when they arrive. A hazard that comes once in a very long while and removes everything is different. It is not the same category of problem as one that breaks a city. Here is the analogy I keep returning to on this. Imagine a stretch of road where a fender bender happens weekly. On that same road, a head-on collision at highway speed happens once a century. By frequency, the fender benders are 99% of your incidents. If you allocated a safety budget by counting events, you would buy parking sensors, but allocate by total harm instead, and the picture inverts completely. Because the rare event takes everything you have in a single moment, and the current allocation of planetary defense is the parking sensor budget. That is not my characterization. The Decadal Survey states it as written policy. Comets allow little warning. the probability is lower. Therefore, asteroids are the priority. I want to be careful here, because I am not calling that wrong. Given a fixed budget and a mandate from Congress, the logic holds. Asteroids are findable decades out, and comets are not. Building the thing that actually works is a rational choice. But it does mean something specific, and you should hear it clearly. The gap is known. It is documented. It sits in the official planning documents of the United States. And the plan for the next decade is to accept that gap. Now hold that, because I want to show you what it looks like. Not in policy language, but in 3 real cases. Cases where it very nearly stopped being theoretical at all. Part 17. 16 days. The first case is the one where the target was a planet. It simply was not us. Comet Siding Spring is catalogued as C2013A1. Robert McNaught discovered it at Siding Spring Observatory in Australia. The date was January 3rd, 2013. At discovery it sat 7.2 astronomical units out, well past Jupiter. Archive searches through Catalina and Pan-STARRS images turned up earlier positions. Those extended the orbital arc backward and improved the solution. And when the early solutions came in, they could not rule out something. A collision with the planet Mars was still inside the uncertainty. Think about the position that puts a person in. You have a comet on an inbound path and a few weeks of observations. Your solution says it might hit a planet with 3 working spacecraft in orbit. Better data narrowed the answer and the nucleus was cleared. But then a second problem emerged behind the first one. Even if the solid body missed, the dust tail might not. Hypervelocity grains would go through a solar panel like it was paper. On October 19th, 2014, Siding Spring passed Mars. The distance was 140,496 kilometres. The uncertainty on that figure was about 4 kilometres. The relative speed was 55.96 kilometres per second. That is less than half the distance from the Earth to the Moon. It is the closest known approach of a comet to any planet on record. NASA's response was to hide the hardware. Mars Odyssey, the Mars Reconnaissance Orbiter, and MAVEN were all manoeuvred. They were positioned so the bulk of Mars sat between them and the debris. The Indian Space Research Organisation did the same with its Mars Orbiter mission. Total interval from discovery to closest approach, about 21 months. Now I want to flag one technical detail from the analysis afterward. David Farnokia and colleagues at the Jet Propulsion Laboratory studied the trajectory. The hardest part of predicting Siding Spring's path was not gravity. Gravity is straightforward and we solved it centuries ago. The hardest part was the non-gravitational acceleration. The comet was outgassing, and outgassing acts exactly like thrust. Thrust changes a trajectory in ways that depend on which vents are active. It depends on how strong they are and where they point as the object rotates. Remember the 16 seconds. Tempel 2's rotation slowing by 16 seconds in orbit, from one small vent near a pole on an 8-kilometre object. That is the same physics, applied to a moving target. It means that even after you find a comet, uncertainty remains. Even after hundreds of position measurements, your prediction carries an error term. An error term produced by the object pushing itself around. There is one more thing about Siding Spring worth stating before I move on. That comet was on a near parabolic orbit with a period measured in millions of years. It has now left, and it is not coming back on any human timescale, which means everything we know about it comes from that single 21-month window. There will never be a second look. There is no future apparition to refine the measurements against. That is the normal condition for these objects. One pass, one dataset, and then nothing forever. Case 2. Comet Hyakutake. Yuji Hyakutake discovered it on the 30th of January, 1996. He found it using a pair of binoculars. Closest approach to Earth came on March 25th, 1996. The distance was 0.102 astronomical units. That is about 15 million kilometres from this planet. Interval from discovery to closest approach, under 2 months. Hyakutake was on a near-parabolic orbit, with a period around 970,000 years. It became the brightest comet in about 200 years. It had the longest tail ever measured on any comet, and a man with binoculars found it 8 weeks before it arrived. Case 3 is the one I think should be far better known. Comet IRAS Araki-Alcock is catalogued as C1983H1. It was discovered on April 25th, 1983 3 separate times. The IRAS satellite found it, as did a Japanese observer named Junichi Araki, and an English amateur named George Alcock found it independently. Alcock found it through the closed window of his own house, using binoculars, sitting indoors. Closest approach to Earth came on May 11th, 1983. The distance was 0.0312 astronomical units. That is 4.67 million kilometres, about 12 lunar distances. It was the closest approach of a comet to Earth in 200 years. Interval from discovery to closest approach, 16 days. 16 days. I want those 3 intervals sitting next to each other in your head. 21 months. 2 months, 16 days, and one more for scale, which many of you saw personally. Comet Neowise, in the summer of 2020, discovered March 27th, closest approach July 23rd of that year. About 4 months of warning. The nucleus measured roughly 5 kilometres across. At perihelion it moved at around 78 kilometres per second. 4 months for a 5-kilometre object at 78 kilometres a second. Now, none of those 4 was on a collision course with anything. All of them missed by comfortable margins, and I am not claiming near misses. I am telling you something more specific, and I think more uncomfortable. In every one of those cases, one interval was short. The gap between the moment humanity knew the object existed and its arrival, between 2 weeks and 2 years. Every time. So the question stops being about probability at all. It becomes a question about capability instead. If one of them had been aimed here, what would we have done with 16 days? Or 2 months? Or even 2 full years? That is the next part. And the answer is much shorter than you expect. Part 18. The rock that came out of the sunrise. On the 15th of February 2013, the world was watching an asteroid. Its designation was 2012 DA14. It was about 30 metres across, and it would pass inside our satellite ring. Every observatory that could point at it was scheduled to do so. That afternoon, it passed at around 27,700 kilometres, closer than the geostationary satellites. Exactly as predicted, exactly on time. The prediction worked perfectly. But that is not what anyone remembers about the 15th of February 2013. Because that morning, 16 hours before the flyby, something else arrived. Over Chelyabinsk, in Russia. And nobody saw it coming. Not one telescope, not one observer, not one automated survey. It came out of the sunrise. The object was roughly 20 metres across, which is small by any standard. It entered the atmosphere at about 19 kilometres per second. And it entered from the sunward direction, which is why it was invisible. At around 9:20 in the morning local time, it detonated. The airburst happened roughly 30 kilometres above the ground. the energy released was equivalent to about 440 kilotons of TNT. That is roughly 30 times the weapon used at Hiroshima. Approximately 1,500 people were injured seriously enough to seek medical attention. Now I want to be precise about how those injuries happened, because the mechanism is not what most people assume. Almost nobody was hurt by anything falling from the sky. The injuries came from glass. The airburst produced a shockwave that reached the ground about 2 minutes later. By then, thousands of people had gone to their windows to look. There had been a brilliant flash across the morning sky, brighter than the sun. It was a completely reasonable thing to do. The shockwave blew in windows across 6 cities. Over 7,000 buildings were damaged in the region. And the people standing at those windows were cut by flying glass. That 2-minute delay is the whole story of Chelyabinsk. Light arrives instantly. Sound and pressure take time to cover 30 kilometres. Everyone had time to walk to a window before the blast reached it. Damage estimates ran to roughly 1 billion rubles at the time, and this was a 20-metre object, small enough that our surveys do not even attempt a complete catalogue at that size. Now put Chelyabinsk next to Tunguska for scale. 1908, 50 to 60 metres across, 10 to 15 megatons. 2,150 square kilometres of forest flattened. 2013, 20 metres across. 440 kilotons, 1,500 injuries, and 7,000 damaged buildings. Triple the diameter, and the energy goes up by a factor of roughly 30. That is because energy scales with volume, and volume scales with the cube of size. Double the width of an object, and you get 8 times the mass. That relationship is why size estimates matter so much in this field, and it is why an object of 10 kilometres is not merely larger than one of 10 metres. It carries 1 billion times the mass. But the number I want you holding from Chelyabinsk is not the energy, it is the warning time, which was 0. Not short, not inadequate. 0, the first anyone knew about that object was the flash, and it demonstrated something we had discussed only in theory, that the sunward blind spot is real, and that objects do come through it. On an ordinary Friday morning, over a city of over 1 million people. There is a second lesson from Chelyabinsk that took years to surface properly. The object turned out to be more fragile than anyone expected. Analysis of the fragmentation showed it began breaking apart high in the atmosphere. It did not hold together and drive downward as a single mass. It came apart, and the breakup is what converted its motion into a blast wave. That fragility is why a 20-metre object produced an airburst rather than a crater. Most of its energy went into the atmosphere rather than the ground, which was, in that instance, considerably better for everyone underneath. But it also means predicting outcomes requires knowing an object's internal structure. An internal structure is the one thing a telescope cannot show you. We learnt that about 67P only by flying there and landing. Now, the natural response is to ask what we are doing about the large ones, and there is a real answer with a date attached to it. On April 13th, 2029, an asteroid named Apophis passes Earth. It is roughly 340 metres across, and it will pass at around 32,000 kilometres, that is inside the ring of geostationary satellites, an object the size of 3 football fields, passing closer than our own communications hardware. It will be visible to the naked eye from parts of Europe and Africa. When Apophis was discovered in 2004, the early solutions were alarming. For a brief period, it carried an impact probability for 2029 of around 2.7%. That was the highest ever assigned to a large object at that time. It reached level 4 on the Torino scale, which had never happened before. Then more observations came in, and the probability collapsed to 0. Radar measurements in 2021 removed any impact risk for the next century, so Apophis is safe, and every agency agrees on that. But hold the shape of what just happened in that story. A large object was found, and the answer changed as data accumulated. And the thing that made the answer trustworthy was a 25-year observation arc. That is the same pattern as Swift-Tuttle, the same pattern as tonight's comet. We resolved Apophis because it comes back, and we could keep measuring it. Which brings me to the question underneath all of this. What happens when the object does not come back? Part 19. What we built and what it cannot touch. Let me start with the good news, because it is real and earned. On the 26th of September 2022, a NASA spacecraft hit something. The mission was called DART, and the target was an asteroid moonlet. Its name is Dimorphos, and the impact speed was about 6.1 kilometres per second. The mission had launched on November 24th, 2021. It struck a target roughly 160 metres across. It did so at a distance of about 11 million kilometres from here, and it changed the moonlet's orbital period more than any prediction had suggested. Lindley Johnson's statement afterward was worth remembering exactly. He said this demonstrates we are no longer powerless to prevent this type of natural disaster. That is a genuine milestone in the history of this species. Humanity moved a celestial body on purpose, and it worked. But look closely at the conditions under which it worked. Every one of them is a condition a long-period comet violates. Dimorphos is small, and it is solid rock throughout. Its orbit was known precisely and had been for years. It was not outgassing, so there were no non-gravitational forces to model, and DART took 10 months to fly to a target 11 million kilometres away. That came after a development program lasting years before launch. Now hold that against 16 days of warning. There is a second data point, more directly relevant and far less discussed, because that one involved an actual comet. In 2005, NASA's Deep Impact mission fired a projectile. It was a 372-kilogram copper impactor. The target was Comet Tempel 1 at 10.2 kilometers per second. Different comet, incidentally, found by the same Wilhelm Tempel, the same man who found the object passing us tonight. The impact produced a spectacular plume and a great deal of science. What it did not produce was any meaningful change in the orbit. The measured change in velocity was around a 10,000th of a millimetre per second. The effect on the comet's perihelion distance was about 10 metres. 10 metres. From a direct hit by a purpose-built impactor. Now, Deep Impact was never designed as a deflection test. It would be unfair to score it as a failed one. It was designed to excavate material and analyse what came out. It did that beautifully, and the science was excellent, but the number tells you something about the physics anyway. Remember the frozen mud ball. Remember the porous, weak, low-density structure I described. When you hit something like that, most of your energy goes elsewhere. It goes into crushing the object and throwing debris around. Very little of it goes into actually moving the thing. This is the difference between hitting a bowling ball and hitting a snowbank. The bowling ball takes your energy and moves away from you. The snowbank takes your energy and simply rearranges itself. Add the outgassing on top of that structural problem. Any deflection attempt on an active comet faces a moving complication. The object is already applying its own unpredictable thrust to itself, and it may respond to being struck by opening entirely new vents. Then it thrusts harder, in a direction nobody chose or modelled. So what is actually being built right now? NEO Surveyor is an infrared space telescope currently in development. Launch is planned for some time after September 2027. It is a genuinely important instrument and will improve our census of dark asteroids substantially, but look carefully at its mandate rather than its capability. It was built to satisfy a congressional requirement about near-Earth objects, specifically to catalogue those 140 metres and larger. Asteroids, it can see comets when they fall inside its field, but it does not close the warning gap Choda's described, and Choda said so explicitly and on the record. Then there is Comet Interceptor, and this one is genuinely clever. I want to explain why, because its design tells you everything. Comet Interceptor is a joint mission between the European Space Agency and Japan. Launch is planned for around 2028 or 2029. It rides on an Ariane 6 alongside the Aerial Telescope. Its lead scientists are Colin Snodgrass and Geraint Jones. They published the mission concept in Nature Communications in 2019. Here is what makes it unusual among all spacecraft ever flown. It launches without a target. The spacecraft flies to the second Lagrange point and parks there. That is a gravitationally convenient spot about 1.5 million kilometres out. And then it waits for up to 3 years. When a suitable, pristine, long-period comet is discovered inbound, it leaves. It departs the parking spot and goes to intercept the target. Now think about why anyone would design a mission that way. You do not build a spacecraft that waits in space for an unknown object, not unless you have accepted something about your own detection capability. The park and wait architecture is not a clever flourish at all. It is an engineering surrender to the warning time problem. It exists precisely because these comets are found too late to plan around. And I need to be completely clear about what this mission is. It is a science mission. It flies past, takes measurements, and gathers data on a pristine object, something that has never been heated by our sun before. That is enormously valuable science, and I do not want to diminish it. It is not a deflection system. It carries no capability to alter anything's trajectory whatsoever. So let me put the full inventory in front of you plainly. Against asteroids, we have a proven kinetic impactor that worked. We have a decades-long survey program with a congressional mandate. We have a dedicated infrared telescope currently in build. And we have warning times measured in years to decades. Against long-period comets, we have one science flyby mission. It has to wait in a parking orbit for a target to appear, and we have a documented warning time of a few months. That is the whole list. There is nothing else on it. Now, before I show you what any of this would look like in practice, I want to take you through the historical record properly, because we have watched this happen already. Not to us, but we watched it in high resolution with every instrument we owned pointed at it. Part 20. The day we landed on one. Everything I have told you about comet structure came from a distance. Telescopes reading light across tens of millions of kilometres. Inferences drawn from brightness curves and dust production rates. Except for one comet. On one occasion. And what we found there changes how you should hear the rest of this. In March of 2004, the European Space Agency launched a spacecraft called Rosetta. Its target was a Jupiter family comet with an awkward name. 67P Churyumov-Gerasimenko. Getting there took 10 years and 4 gravity assists. 3 from Earth, 1 from Mars. The spacecraft then spent 31 months in hibernation to save power. It woke up in January of 2014 and arrived in August. Rosetta did not fly past. It went into orbit around the nucleus. Then it stayed there for over 2 years, riding alongside as the comet approached the Sun. That is the mission profile CRAF was supposed to fly at Tempel 2. 2 decades later, a different agency flew it at a different comet. And in November of 2014, Rosetta dropped a lander onto the surface. The lander was called Philae, and its descent did not go as planned. Harpoons meant to anchor it failed to fire. Philae bounced. It bounced twice, the first time nearly a kilometre back off the surface. It came to rest in a shadowed crevice, where its solar panels could not charge. It operated for about 60 hours on battery power, and then fell silent. That partial failure still produced the only surface measurements we have of any comet. Now here are the numbers that matter for everything else tonight. The nucleus of 67P has a bulk density of about 0.5 gram per cubic centimetre. Water is 1 gram per cubic centimetre, which means this object is roughly half the density of water. It would float. If you could find an ocean large enough, a comet would float in it. The reason is porosity. The interior of 67P is estimated to be 70 to 80% empty space. Not solid rock with some gaps. Mostly gaps, with some solid material distributed through them. Think of a meringue rather than a stone. Or think of a snowdrift that has been sitting for a season. There is structure there, and it holds its shape, and it is almost nothing. Philae's own landing supplied a second data point about that structure. Where it first touched down, the surface was soft. Where it finally came to rest, the material was significantly harder. The comet was not uniform. It had a soft dusty covering over something more rigid, and the shape was the third surprise. 67P is not a potato. It is 2 lobes joined by a narrow neck. Astronomers immediately started calling it the rubber duck. The current explanation is that it is a contact binary. 2 separate objects that drifted together at low speed and stuck. Not a collision. A merger at walking pace, sometime in the early solar system. Now put those 3 findings against the deflection problem I described earlier. You are trying to change the trajectory of an object with the density of a meringue. It is 70% empty inside. It may be 2 objects held together loosely at a narrow join. And its surface hardness varies from place to place unpredictably. Hit that with a kinetic impactor, and the outcome is genuinely hard to predict. You may transfer momentum efficiently. You may punch straight through a void. You may snap the neck of a contact binary and create 2 problems. DART worked because Dimorphos was a solid rubble pile of rock. Rosetta showed us what the other kind of target actually looks like. There is one more result from Rosetta I want to give you, because it changed a story that had been told for decades. For a long time there was a hypothesis about where Earth's water came from. The young Earth was too hot to retain much water during formation, so the oceans in this account were delivered afterward, by comets bombarding the surface over hundreds of millions of years. It is an appealing idea, and it has been in textbooks for a generation. Rosetta carried an instrument capable of testing it directly. The way you test it is through deuterium. Deuterium is a heavy form of hydrogen with a neutron in the nucleus. Some fraction of the hydrogen in any water is deuterium instead, and that fraction acts like a fingerprint for where the water formed. Water formed further from the sun tends to carry more deuterium. Measure the deuterium ratio in a comet and compare it to Earth's oceans. If they match, the comet hypothesis gains enormous support. If they do not, something else delivered our water. Catherine Altweg of the University of Bern led that instrument team. The result, published in Science in December of 2014, was decisive. The deuterium ratio at 67P was roughly 3 times that of Earth's oceans. Not a close match, not within the uncertainty. 3 times. That single measurement significantly weakened the comet delivery hypothesis. Current thinking leans toward asteroids from the outer belt as the primary source. Comets may have contributed something, but they are unlikely to be the main answer. I bring this up for a reason that goes beyond the water itself. We had a confident story about the origin of Earth's oceans. it survived for decades on indirect reasoning and plausibility. Then one instrument, on one spacecraft at one comet, undermined it. That is what happens when you finally reach one of these things. And we have reached exactly one. Everything we believe about the other 4,000 known comets rests on inference, including everything I have told you tonight about the object passing overhead. Part 21. The options nobody has tested. I told you the inventory against long-period comets is one science flyby. That is accurate for hardware that exists, but it is not the whole conversation, because other techniques have been studied. None of them have been tested. Some of them have serious problems. I want to walk through them anyway, because the gaps are instructive. The first alternative is the gravity tractor. The idea is elegant. You fly a heavy spacecraft alongside the object and simply hold position. You do not touch it. The mutual gravitational attraction between spacecraft and object does the work. Over months or years, that faint pull alters the trajectory measurably. The advantage is that it works regardless of what the object is made of. Structure does not matter. Porosity does not matter. You are pulling on mass, and mass is mass. For a fragile, 70% hollow comet, that is exactly the right property. The problem is time. A gravity tractor is a gentle technique by design. Published concepts require years of station keeping to produce a useful deflection. Some require a decade. Against an asteroid found 20 years out, that is workable. Against a comet found 9 months out, it is meaningless. The second option is the ion beam shepherd. You fly alongside and fire an ion thruster at the object rather than pulling it. It is faster than gravity, but it has the same fundamental constraint. It needs time you do not have. The third option is the one everybody thinks of first. Nuclear. Let me be careful here, because the popular version of this is wrong. The technique that has been studied seriously is not blowing the object up. Fragmenting a large object into pieces is generally considered a worse outcome. You convert one tracked threat into many untracked ones on similar paths. What has been studied is called a standoff burst. You detonate a device near the object rather than on it. The radiation flash heats one side of the surface intensely. That surface layer vaporizes and blows off, and the material blowing off acts as a rocket, pushing the object the other way. The physics is sound, and the energy density is far higher than anything else available. For a short warning scenario, it is the only technique with a plausible timescale. But look at the problems in order. The first problem is that nobody has ever tested it. Not once, on any object at any scale. Every estimate of its effectiveness comes from simulation, and the simulations depend heavily on assumptions about the target's structure, which, as Rosetta demonstrated, we mostly do not know. The second problem is the same structural issue from earlier. A porous, low-density object responds differently to a shock than a solid one. The vaporized layer may not couple efficiently to the bulk, or the object may simply come apart under the load. The third problem is legal and political. The Outer Space Treaty of 1967 prohibits placing nuclear weapons in orbit. The treaty language was written for a different purpose entirely. Whether planetary defense falls under it is genuinely disputed among lawyers. And the practical version of that problem is worse than the legal one. A nuclear device on a launch vehicle in an international emergency requires agreement between governments that would need to trust each other's intentions completely, on a time scale of weeks. The fourth problem is the one I keep coming back to. Delivery, whatever the technique, you still have to fly there. DART took 10 months to reach a target 11 million kilometres away. A comet inbound at 50 kilometres per second is a much harder intercept. There is a decision problem sitting on top of all four techniques, and it is not technical. Every one of them requires committing enormous resources to a probability, not a certainty. Remember how the Apophis story ran? An early solution gave a real impact probability, and then it collapsed to zero. That is the normal outcome. Almost every scare resolves that way once more data arrives. So imagine the position of anyone making the call in a real event. You have an object, a preliminary solution, and a probability that will likely drop. Acting immediately costs a great deal and will probably prove unnecessary. Waiting for certainty costs the only thing that actually matters, which is time. Against an asteroid found decades out, you can afford to wait for better data. Against a comet found 9 months out, waiting is the decision. So let me total this honestly. Gravity Tractor works on fragile objects and needs a decade. Ion Beam Shepherd, the same, with slightly better numbers. Kinetic Impactor is proven, and it is proven on the wrong kind of target. Nuclear Standoff is the only fast option, and it is untested, legally contested, and structurally uncertain. That is the complete menu. Not one item on it is both fast and demonstrated. And I want to be clear that this is not a secret. None of what I have described is classified or suppressed. It appears in published studies, in agency planning documents, in the Decadal Survey. Anyone can read it this evening. It is simply not discussed. And the reason is straightforward. There is no news event attached to it. Nothing is happening right now. There is no object with a designation, no date on a calendar, nothing to photograph. Which is the defining problem with a hazard whose main feature is that you do not see it coming. It generates no coverage until it generates nothing but coverage. Now, I have spent a long time on what we cannot do, so let me be fair and state clearly what we can. Against the population that actually threatens us most often, we are in good shape. Near-Earth asteroids above 1 kilometre are close to fully catalogued. None of the known ones threatens us in the next century. The survey work continues every clear night from multiple continents. And DART demonstrated that a deflection is achievable with sufficient warning. That is a genuine achievement, and it happened inside a single human lifetime. 50 years ago, none of it existed. The gap is specific rather than general. It is not that we are defenceless, it is that our defences are built around a property that one category of object does not have. They come back. That is the property. Everything depends on it. Part 22. The week we watched a planet get hit. On the 24th of March, 1993, 3 people found something wrong. Carolyn Shoemaker, her husband Gene Shoemaker, and David Levy were at Palomar Observatory. They were working with a small 46cm Schmidt telescope. What they found was not a point of light with a tail, it was a line, a row of separate objects strung along a single track. Each one had its own small tail, and they all moved together. Somebody described it as a string of pearls, and the name stuck permanently. They had found Comet Shoemaker Levy 9, and it was in that condition for a specific reason. In July of 1992, it had passed inside Jupiter's Roche limit. The Roche limit is a distance rather than a barrier. It is the distance where tidal force exceeds the force holding a body together. Get closer than that, and the object does not fall onto the planet. It gets pulled apart instead. The near side is being tugged harder than the far side. A weakly bound object cannot survive that difference in force. Shoemaker Levy 9 came apart into more than 21 identifiable fragments. Then the orbital analysis came back and told everyone the ending. The fragments were not going to escape Jupiter's gravity at all. They were going to come back around and go into the planet. Between the 16th and the 22nd of July, 1994, they did. One after another, over 6 days, 21 pieces fell in. They arrived at about 60 kilometres per second each. Every telescope on Earth was watching that week. The Galileo spacecraft was in flight with a direct view of the impact side. Hubble was watching from orbit. This was the first time in history a collision was predicted and then observed. Now the numbers, and I want you to take these slowly. Fragment A was one of the smaller ones, roughly 2 kilometres across. It released energy on the order of more than 1 million megatons. Fragment G was the largest of the group. It released roughly 6 million megatons of TNT equivalent. The fireball reached around 24,000 Kelvin at its peak. That is about 4 times the surface temperature of our own Sun. The largest impact plume rose approximately 3,000 kilometres off the planet. It left a dark scar in Jupiter's atmosphere, comparable in size to Earth. Total energy from the sequence exceeded every nuclear weapon on this planet combined, several times over. I want to be honest about what that scar actually was. It was atmospheric, because Jupiter has no surface to crater. Within months the winds had erased every trace of it. Jupiter did not care in the slightest. But we cared enormously, and that is the point of this section. Until July of 1994, the impact hazard was an abstraction. It was a thing people argued about in journals. There was a geological record, and there were craters on the moon. But no living person had ever watched a large impact happen. Then for 6 days, everybody watched one, in colour, on the evening news. The line from that week to today's institutions is direct and traceable. The SpaceGuard survey effort accelerated afterward. Congressional mandates followed within a few years. The Planetary Defense Coordination Office at NASA exists downstream of that week. DART exists downstream of that week. The modern architecture of planetary defense has one origin. It was built in response to watching a comet do what comets do. And then we spent the next 30 years building tools for asteroids. Stay with me, because I want to bring this back to the ground now, to the 2 events people actually reach for when they discuss impacts. Part 23. What water does. I have spent this briefing talking about impacts as energy numbers, megatons, kilometres per second. Times Chicxulub. Those figures are accurate, and they are also abstract. So let me talk about what actually happens when something arrives. Because the answer depends almost entirely on where it lands. Roughly 71% of this planet's surface is ocean, which means that for any object arriving at random, the odds favour water. Somewhere around 7 times in 10, an impact happens at sea. Most people hear that and treat it as good news. Open ocean, far from anyone, nothing to destroy. That instinct is wrong, and the reason is worth understanding properly. Water does not absorb an impact, water transmits it. When an object strikes land, most of the energy goes into the ground. It excavates a crater, pulverizes rock, and throws material into the atmosphere. The devastation is enormous, and it is also localized. Distance from the impact point protects you fairly quickly. Water behaves completely differently because it is a fluid. An impact does not make a permanent hole in the ocean. It makes a temporary one, and then the ocean closes it. That collapse sends a wave outward in every direction at once. And here is the property of ocean waves that matters most. In deep water, they lose very little energy over distance. A tsunami crossing open ocean can travel thousands of kilometres. It arrives at a distant coastline carrying much of what it started with. Think of the difference between punching sand and punching a full bathtub. The sand takes the blow and keeps it in one place. The bathtub sends the water over the sides on all 4 edges. In deep ocean, a tsunami is almost imperceptible at the surface. The wave height might be under a metre, spread across a wavelength of hundreds of kilometres. a ship would not notice it passing underneath. But the energy is not in the height, it is in the volume of water moving. When that wave reaches a continental shelf, the physics changes. The seafloor rises, the water column compresses, and the wave slows down. The energy has to go somewhere, so it goes upward. The wave height climbs steeply as it approaches the shore. We have observed exactly this behaviour from earthquakes, which do something similar. In 2004, the Indian Ocean tsunami killed roughly 230,000 people, across 14 countries. Many of the deaths happened thousands of kilometres from the earthquake itself. In 2011, the Tohoku tsunami killed close to 20,000 people in Japan. Neither of those came from an impact. Both came from the seafloor moving. An impact from a large object delivers substantially more energy than either earthquake, and it delivers it into the water column directly rather than through the crust. Now, I want to be honest about the limits of the modelling here. This is an area of genuine scientific disagreement. Some studies suggest impact-generated tsunamis behave differently from earthquake tsunamis. The wavelengths are shorter, and shorter wavelength waves dissipate faster in deep water. If that holds, the reach of an impact tsunami may be smaller than early models predicted. Other work suggests the opposite for larger objects. The disagreement is not settled, and I am not going to pretend it is. But there is a second effect that is not in dispute at all, and it is the one that scales worst. Vaporized seawater goes into the upper atmosphere. An impact energetic enough will inject an enormous quantity of water vapor into the stratosphere, along with dust and salts and whatever the object itself was made of. Water vapor is a greenhouse gas. Dust blocks sunlight. Those two effects work in opposite directions and on different timescales. The dust cools the surface first, over months to years. The water vapor warms it afterward, over years to decades. Which means the climate consequence of an ocean impact is not one event. It is a sequence of them, running in different directions. And this is the thread that connects back to Chicxulub. The object 66 million years ago did not strike open ocean. It struck a shallow carbonate platform in what is now the Yucatan. That geology mattered enormously. Carbonate rock, when vaporized, releases carbon dioxide. The region also held sulfate-rich deposits, which released sulfur compounds. Those sulfur aerosols are what drove the immediate global cooling. Estimates of the resulting temperature drop run into many degrees, sustained for years. The extinction was not caused by the impact itself. It was caused by what the impact put into the air, and what it put into the air depended on the rock it happened to hit. Which means the single most consequential event in the history of complex life had a variable in it. Where it landed. That is an uncomfortable thing to sit with. The same object, arriving minutes earlier or later, hits different ground. Deep ocean instead of a shallow carbonate shelf. A granite continent instead of a sulfate basin. The outcome changes, possibly enormously. I raise this because it reframes what a warning time is actually for. If you cannot deflect an object, warning time still has value. Knowing where an object will strike weeks in advance is not nothing. It is the difference between evacuating a coastline and not evacuating it. It is the difference between stockpiling food and improvising afterward. Paul Chodas said 2 years is really short unless you have prepared a lot on the ground. That phrase covers everything I have just described. Ground preparation is not a consolation prize when deflection fails. For most realistic scenarios, it is the entire response, and it requires knowing something specific about where and when, which is the one thing a long-period comet is least likely to give us. Part 24. The Forest That Fell and the Argument Nobody Has Closed. On the 30th of June, 1908, something detonated over Siberia. The time was around 7:17 in the morning local, the place was above the Podkamania-Tunguska River. It did not hit the ground at all, it exploded in the air, somewhere between 5 and 10 kilometres up. The energy released ran somewhere in the range of 10 to 15 megatons. Some estimates push that as high as 20 megatons, roughly 1,000 times the weapon used at Hiroshima. It flattened 2,150 square kilometres of forest. That is 830 square miles of standing timber. Approximately 80 million trees went down that morning, and the way they went down is the detail that identifies the cause. They fell in a radial pattern, pointing outward from a single central point, like the spokes of a wheel laid flat on the ground. At the very centre, trees were left standing but stripped completely bare. Every branch was gone because the blast wave came straight down on them. Nobody died as far as the surviving record shows. That is entirely an accident of geography and nothing else. Central Siberia in 1908 was among the emptiest places on Earth. Put that same event over a European capital and the century looks different. The consensus explanation is a stony asteroid roughly 50 to 60 metres across. NASA holds that position, and modelling work supports it. Christopher Chiber and colleagues published the key analysis in Nature in 1993. 50 metres. That is the height of a modest office building, and that is what it takes to flatten an area the size of a city. But there is a comet hypothesis, and it has never entirely gone away. I want to represent it fairly rather than dismiss it out of hand. The argument for a comet rests on two observations. First, no crater and no conclusively identified fragment was ever recovered. That is what you expect from an icy body that vaporized completely. A stony object should leave something behind. Second, and more interestingly, the night skies afterward were wrong. For several nights across Europe, they were abnormally bright. People in London reported reading newspapers outdoors at midnight. That is consistent with water vapour and fine ice injected into the upper atmosphere. It forms what we now call noctilucent clouds. The mainstream position remains asteroid, and the modelling works well. Stony objects can and do disintegrate completely under the right conditions. But the comet reading is a minority scientific position, not a fringe one. The honest statement is that the identity is not fully settled, not after 118 years of investigation, which brings me to the larger version of the same argument. 66 million years ago, an object struck what is now the Yucatan Peninsula. It measured roughly 10 kilometres across. It left a crater between 150 and 180 kilometres wide. The consensus was established by the Alvarez team in 1980. Their evidence was a global iridium layer in the rock record. The impactor was an asteroid, specifically a carbonaceous chondrite. Work by William Bottke and colleagues in 2007 proposed an origin. A collision in the Baptistina asteroid family sent fragments toward the inner solar system. That is the textbook answer, and it remains the majority position today. In February of 2021, a paper appeared in Scientific Reports. Amir Siraj and Avi Loeb at Harvard proposed something different. Their argument was that a long-period comet could explain it better. The mechanism they described should sound familiar to you now. A comet falling in from the Oort cloud passes very close to the Sun. Inside the Sun's Roche limit, it is tidally disrupted. Exactly the way Jupiter disrupted Shoemaker-Levy 9. It shatters into fragments of around 7 kilometres each, and one of those fragments strikes Earth. They argued this mechanism raises the effective cometary impact rate substantially, by roughly a factor of 15. And they argued a cometary composition fits the geochemistry better. The pushback was immediate and substantial. Stephen Desch, Alan Jackson, Jessica Noviello and Ariel Ambar responded formally. They published in Astronomy and Geophysics in 2021. They followed with the matters arising in scientific reports in 2022. Their objections were specific rather than general. The fragment count in the Suraj and Loeb model was too high, tens of fragments rather than thousands in their analysis. The paper conflated different subtypes of carbonaceous chondrite. That undermines the compositional argument at its foundation, and it did not adequately account for the iridium layer itself, which remains the original and still the strongest piece of evidence. Their conclusion was that a carbonaceous asteroid is strongly favoured, and that a cometary origin can likely be ruled out. Suraj and Loeb replied in 2022, defending their rate calculation. They argued it holds to within a factor of about 7. I am walking you through this dispute rather than picking a side, and the reason is what it demonstrates about certainty. The consensus is asteroid. I want to state that plainly before I go further. Nobody should leave here thinking I said otherwise, but serious researchers at serious institutions were arguing about it in 2022, about the single best studied impact event in the geological record, with 66 million years of accumulated evidence available, and a physical crater we can drill into and sample directly. We cannot definitively agree on whether that object was a comet or an asteroid. That is with unlimited time and a crater to examine at leisure. Now hold that against 6 months of warning and a moving target. Part 25. 9 months and nothing on the pad. I want to do something concrete now, because description only takes you so far. The shape of this problem becomes clear when you try to solve it. So let us run it as a scenario. A survey telescope picks up a moving object at 5 astronomical units. Follow-up observations over 2 weeks tighten the orbital solution, and the solution says it arrives at Earth's position in roughly 9 months. The object measures 4 kilometres across. What happens next? The first thing that happens is nothing, and people underestimate this badly. An orbital solution from 2 weeks of observations is not precise enough to act on. The uncertainty region around the predicted position is enormous. What you have is not a prediction of impact at all. You have a probability, and it will move around for weeks. New observations come in and it shifts, and it will very likely drop to 0, because almost every scare resolves that way. That is not incompetence. That is exactly how the process is supposed to work, but it consumes calendar time you do not have. Call it a month, optimistically, before anyone says the word out loud. You are now at 8 months. The second thing that happens is a discovery about your own toolkit. You cannot use the thing you built. DART worked because a spacecraft was designed, built, tested and launched over years. Then it flew for 10 months to reach a target 11 million kilometres away. There is no kinetic impactor sitting in a warehouse ready to go. Nobody keeps one on a shelf. Even if one existed, the flight time to reach an inbound comet is substantial. It is a real fraction of the time you have remaining, and you would be launching into a trajectory that has to match something moving at 50 kilometers a second. Say a national laboratory pulls something together on an emergency footing. The most optimistic published timelines for a crash program run around a year, and that assumes a mission profile studied in advance. You are now past your deadline before the vehicle physically exists. But suppose everything goes right and you get something off the ground. Suppose you put a mass on an intercept course successfully. Now you meet the physics problem I described earlier. Your target is a frozen mud ball, porous, weak, structurally incoherent, with a density below water. When you hit it, most of your energy goes into crushing and excavating. That is what Deep Impact demonstrated in 2005. 372 kilograms at 10.2 kilometers a second. The result was a velocity change of a 10,000th of a millimetre per second, and a perihelion shift of about 10 metres. To deflect something away from Earth, you do not need to move it far. You need to change its arrival time by a few minutes. Miss by 4 minutes, and you miss by an entire Earth diameter, but the further out you apply that change, the less change you need. The whole logic of deflection depends on years for a nudge to accumulate. With 6 months of lead time, a tiny nudge stays tiny. And there is a worse possibility hiding behind the obvious one. You might succeed at breaking it apart. Take a weakly bound object and hit it hard enough to matter. You may not get a deflected comet at all. You may get several fragments on slightly different paths, most of which are still headed exactly where the original was headed. You have converted one problem into a distributed one. Then there is the wildcard I have mentioned 3 times tonight. The object is outgassing while you aim at it. Every calculation above assumes you know where the comet will be, but an active comet applies thrust to itself continuously and unevenly. That is not a theoretical concern in any way. It is the specific thing that made Siding Spring's path hard to predict. Farnocchi's team at the Jet Propulsion Laboratory identified it directly, and it is the same physics slowing the rotation of tonight's comet. 16 seconds every orbit, from one small vent near a pole, measured across 3 apparitions spanning 22 years of observation. Remember what that number represents. Gentle, continuous, off-center thrust, applied to a mountain. Given enough time, it visibly changes how that mountain spins. Now put that physics on an object you are trying to hit, at closing speeds of tens of kilometres per second. Where your aim point must be correct months in advance, and where hitting it may open new vents nobody modelled. So let me answer the question I set up at the start of this. With 6 months of warning against a 4-kilometre long-period comet, the assessment is clear. There is no established capability to deflect it, not because the physics is impossible in principle, because the schedule does not permit building and flying the thing, and because the target is the wrong kind of object entirely, wrong for the one technique we have actually proven works. What you would do instead is what NASA did at Mars. During Siding Spring, they moved what could be moved, and they prepared on the ground for what could not, which is exactly what Paul Chodas meant with that phrase. 2 years of warning is really, really short unless you have prepared a lot on the ground. Look carefully at the second half of that sentence. He is not describing deflection at all. He is describing civil preparation for an impact you have accepted. That is the current state of the art, stated by the person who runs the office responsible for it. And now I want to close a loop I opened an hour ago, because there is one more category of object I have not told you about, and we only found out it existed 9 years ago. Part 26. The one we found on its way out. On the 19th of October, 2017, the Pan-STARRS telescope found something. It was in Hawaii, doing routine survey work, and the object it found did not behave correctly. Everything in the solar system moves on an orbit bound to the sun, circles and ellipses, closed loops that come back around. Even a long-period comet from the Oort cloud is bound to us. It comes in, swings around, and goes back out. Its path is a very stretched ellipse, but it is still an ellipse. This object's path was not an ellipse at all. Its eccentricity measured above one. In orbital mechanics, that means the path is a hyperbola. It is not a closed loop of any kind. The object was not falling in from the outer solar system. It was passing through, from somewhere else entirely. It would leave, and it would never return. It was named Oumuamua, and it was the first object from another star system ever observed here. It was small, a few hundred meters, and extremely elongated in shape. It produced no visible coma at all. It also showed a small acceleration gravity alone could not explain. That triggered several years of argument that has not fully closed. 2 years later, in August of 2019, an amateur found the second one. Gennady Borisov, working in Crimea, spotted it. 2I Borisov was also on a hyperbolic path out of the system, and this one was unambiguously a comet, with a coma and a tail. Its composition looked broadly similar to our own comets, with some notable differences in carbon monoxide abundance. Then a third arrived, catalogued as 3I Atlas. It has been tracked over the past year, and is now heading back out. 3 objects from 3 different origins in 8 years. Now here is why that matters for everything I have said tonight. Before 2017, interstellar objects were a purely theoretical population. Astronomers assumed they existed, and the reasoning was sound. If planetary systems eject material during formation, and every star does that, then the galaxy should be full of loose debris drifting between stars. But nobody had ever actually seen one. And with no detections, the estimated density of that population was a guess. 3 detections in 8 years changes the arithmetic completely, especially given that survey telescopes only recently became capable of finding them. It implies the population is not small at all. And an interstellar object is the long-period comet problem, worsened, every dial turned further up. It is not bound to the Sun in any way. So it does not arrive at the 50 to 70 kilometres per second of an Oort cloud comet. It arrives with whatever velocity it already had relative to our star. Then it adds our Sun's acceleration on top of that. It comes from any direction whatsoever, with no relationship at all to the plane of the solar system, and it is discovered when it is already inside the orbit of Jupiter. Because that is where an object that's small becomes bright enough to catch. Oumuamua was discovered after it had already made its closest approach to the Sun. We found it on the way out. Let me say that again, because it is the most important sentence here. The first interstellar object ever detected was found after closest approach had happened. The decadal survey I quoted earlier does mention these objects. The wording groups them with long-period comets deliberately. Both allow little warning time for mitigation efforts, it says. They are grouped together for exactly the reason I just described. And this is where Comet Interceptor becomes genuinely important. Not merely clever. Its target list explicitly includes interstellar objects. That mission waiting in a parking orbit for 3 years is the only hardware. The only thing anyone has designed that could reach one while it is here. One science flyby. That is the complete human response to a new class of object. Arriving from outside the solar system at unbounded velocity. From arbitrary directions. With negative warning time. I want to be measured about this, because the numbers still say what they say. The probability that any given interstellar object hits Earth is vanishingly small. The solar system is enormous and mostly empty space. Earth is a very small target moving through a very large volume. Nothing about 3 detections in 8 years constitutes a threat to anyone. But the category existed for the entire history of our species. And we did not know. We found out in 2017. The instruments that found it are the same ones Chodas described, the ones that will not give us meaningfully better warning on comets. So hold the 2 things together before we finish. Tonight, a comet we have tracked for 153 years passes on schedule. At a distance we calculated decades in advance, to within a few thousand kilometres. And in 2017, an object from another star came and went. We found it on the way out. Part 27. What happens over the next few weeks? Let me come back to the sky above you, because I owe you a forecast. Over the coming nights, Tempel 2 begins to recede from us. The geometry that made this apparition favourable is already unwinding. Both its distance from the Sun and its distance from Earth increase now. It will fade through the rest of August and into September steadily. It continues moving out through Pisces Austrinus, staying a southern object throughout. If you want to see it, the window is this week rather than next. Then, 8 days from now, the 12th arrives with 3 separate events. The Perseids peak under a new moon, with rates expected somewhat below normal. Totality crosses Greenland, Iceland, northern Russia, Spain and a corner of Portugal. And Tempel 2 continues quietly outbound, unremarked. Its next aphelion falls on April 12th, 2029. It comes back in about 5.5 years from tonight. The geometry then will be worse than this year's. The next apparition resembling tonight is a long way out. Now, 2 branching scenarios, and one is far more likely than the other. The first scenario is that nothing further happens at all. The comet fades on schedule, and the light curve behaves as modelled. Observing reports from the Comet observation database come in matching the forecast. In that case, the valuable science from this apparition is already recorded. The trail imagery from the plane crossing in July, and the continued rotation measurements, which answer a specific question: whether the spin down is still running at 16 seconds per orbit, or whether that rate has changed since 2010. I find that second question genuinely interesting, and here is why. If the rate is constant, the active vent is stable across decades. If the rate is shifted, something on that surface has changed. A vent has closed, or opened, or moved. We would be watching the geology of an 8-kilometre object change. From 62 million kilometres away, using nothing but the timing of its brightness variations. The second scenario is that the comet does something unexpected. I want to be clear that this is not manufactured drama. Comets outburst. They brighten by several magnitudes within hours, for reasons nobody predicts. Tempel 2 has structured arcs in its Spitzer imagery from 2010. Those suggest discrete events rather than steady sublimation, and its brightness forecasts spanned 3 full magnitudes before it even arrived. If it outbursts, the object becomes considerably easier to observe, and the observing community finds out the way it always does. Somebody at a telescope notices it looks wrong and files a report. There is no mechanism by which either scenario threatens this planet. The minimum orbit intersection distance is 0.407 astronomical units. That number does not change based on how bright the comet gets. What I am actually watching for is something else entirely, and I want to tell you what would move this story. If a new long-period comet is announced inbound in the coming weeks, everything changes. This stops being a historical briefing and becomes a live one. The announcement would come through the Minor Planet Center, in the form of an electronic circular distributed to observers worldwide, and depending on the geometry, the interval between that circular and closest approach is short, measured in months, exactly as Yeomans described. That has happened before, repeatedly in the cases I walked you through. It will happen again. It is very likely happening somewhere in the outer solar system right now. The object is currently too faint and too far for anything we own to detect, which means the most consequential fact about the next few years is unavailable tonight, not classified, not disputed, simply not yet visible. Part 28. The ones that never come back. Tonight an object 6.6 miles across passes 62 million kilometres away, dark as burnt coal, mostly dead. Trailing a river of grit laid down over centuries, we have known it was coming since 1873. We know its size to plus or minus 40 metres. We know its rotation period to 1,000th of an hour. We know that period is lengthening by 16 seconds every single orbit. We know its surface reflects 2.2% of the light reaching it. That knowledge represents 153 years of continuous human attention, 5,900 observations made by thousands of people, most of whom never met each other, many of whom died before the picture was finished. And every piece of it was possible for one reason. Jupiter caught this object and put it on a short orbit, somewhere we could watch it come around again and again. That is what safety actually looks like. Safety is not distance from a threat. Safety is a long observation arc. Swift-Tuttle proves the same point from the other direction, 16 miles across, coming at us retrograde at 60 kilometres per second. Its orbit passes within a third of the Earth-Moon distance of ours. Donald Yeomans estimated an impact at 300 times the energy of Chicxulub. And nobody loses sleep over it. Because Marsden and Cronk matched it to Chinese records from '69 before the Common Era. Once you have a 2,000-year arc, the future stops being a question, and there is one more piece of that ledger worth stating plainly. Tempel 2 has been observed at 24 of its 29 returns, which means 5 times we lost it. The geometry was wrong and nothing could be pointed at it. Even the object we know best has gaps in its file. Even the comet on the leash went unwatched for years at a stretch. So here is the shape of everything I have shown you tonight. Every object we are relaxed about for one reason. Somebody watched it for a very long time, and the objects we cannot watch for a long time, we are not relaxed about those. We are simply not looking. Which brings me back to where this started. If we can see a 6-mile comet coming from 153 years away, why are the ones we cannot see the ones that could finish us? I have looked for a satisfying answer, and I do not have one. The closest I can get is this. Everything about our confidence is built on repetition. We understand the objects that come back to us. Our surveys, our impact emissions, our catalogues, all of it depends on that. An object has to show up more than once, so we can measure it, refine the orbit, and plan. An object that only comes once defeats every single piece of that. Not because it is bigger or faster, although it is both. Because it never gives us the second look that everything we know requires. Tonight, 62 million kilometres away, a very old comet passes on schedule. It has come back 30 times. It is the safest thing in the sky for exactly one reason. People have been paying attention to it without interruption since 1873. Somewhere past the orbit of Jupiter, something is falling inward right now. An object nobody has seen, on a path nobody has calculated. It will get a name for the first time some morning in the next few decades. When a survey telescope picks up a moving dot and the software flags it. Whether that morning is interesting or catastrophic depends on numbers nobody has measured. Go outside tonight if your sky is dark and your binoculars are good. It sits low in the south. Faint, and it looks like almost nothing. 161 lunar distances away, 6.6 miles wide. On time for 153 years. It is the ones that are not on any schedule that I keep watching for.